a quick one before we get started. I hope all of you slept well yesterday night, and how many of you are leaving today, returning today? Okay, and how many of you are returning tomorrow or later? Okay, so I guess you have a good opportunity to explore the campus in that case. How many of you went to the Nehru Museum over here on campus? Any of you went there? You went? Okay. When did you go? Yesterday, what, evening? Are they open on Saturday or? Okay, okay. All right, let's get started. Good morning. So, we are on the very last leg of our Gyan course on advances in multiphase flows. So, the plan for today is I will sort of summarize all the microscale and nanoscale activities that we are doing and contrast it with what others are doing in the literature. And then in the afternoon, Dr. Bhattacharya is going to present boiling on porous surfaces, and then after that I guess there is a quiz for about 30 minutes. Hopefully you should be able to do it in 15 minutes. It's not that complicated. It's objective type yes no quiz, and then after that we have the closing ceremony. Okay, so that's the plan for the day. So I wanted to highlight the use of multiphase flows in nanomanufacturing, particularly for things like energy storage, for cooling or thermal management, and also for sensing. Okay, it's micro and nanoscale temperature sensing or flow sensing and so on. All right. So before I get there, I just wanted to give you an overview of Texas A&M. That's where I'm coming from now. Even though my basic undergraduate engineering education was here at IIT Kharagpur. So a little bit about the campus. This is an aerial overview of Texas A&M. This is our main building. Texas A&M is probably the only university that you enter through a golf course. Okay, so we have a golf course over here. The university has its own airport, and so the airport is way in the back over here. And then mechanical engineering, my office, let's see, is over here essentially. So that's our mechanical engineering building. All right. So in terms of our department, we are close to, this is a little bit old slide, we are close to about 1500 undergraduate students now, and our plan is to grow to about 2000 undergraduate students in the next 5 to 7 years or so. And then in terms of our faculty, currently we are close to I think about 55 faculty. Our plan is to grow to somewhere between 60 and 65 faculty members in the department. And then in terms of the different areas of research that's going on in our department, these are the different topics that we are working on, both fundamental and applied. And then in terms of our campus, we also have a campus in Doha in Qatar. So Texas A&M has a degree granting institution at this location. And then in terms of our my own research experience, I think I talked a little bit about it on the first day, so I will skip this one. And in terms of my presentation today, I am going to talk a little bit about this nanomanufacturing platform called Dept nanolithography, and then after that I am going to primarily focus on cooling and thermal storage, particularly with respect to applications in solar thermal energy involving molten salts. But there is also a lot of application of this in nuclear power as well, particularly with respect to high temperature storage. Okay, and so that means I'll talk a little bit about pool and flow boiling, and then a good amount of time I will spend on talking about nanofluids. Okay, and then as I mentioned on the first day, we encountered some very counterintuitive data. For example, we found that lower thermal conductivity nanofluid was giving us higher critical heat flux in boiling, and to resolve that we had to resort to molecular dynamics. So I'm going to talk a little bit about molecular simulations, and then focus more on the results we got from the molecular level simulations in our research activities. And then as I mentioned on the first day, you should not take things for granted. Both within our group and outside our group, we are constantly having to justify why we are using nanotechnology or microtechnology in multi-phase flows, and what type of nanoparticles are we going to use that gives us the best performance, where do we use it, do we use it in the ice box, do we put it in the refrigerant in a HVAC system, for example, and then which type of nanomanufacturing platform should you choose, and then how nano do you go. Okay, and so remember I asked you all these questions on the first day, that by the end of the course I'll ask you the question, how nano should we go. Okay, so let's see if you can figure that out, but if you can't, that's fine. We can discuss that design question explicitly a little later. Okay. So in terms of, as I mentioned on the first day, my students do all the hard work. I get to come and do all the fun stuff, do the presentations. Particularly, as I mentioned, we academicians are on the dark side of Star Wars. So we like to make clones, and these are my clones, Dr. Shin and Dr. Singh, who contributed in a big way to what I'm going to be showing in this presentation today. So in terms of my presentation today, I'm going to be focusing on boiling on nanostructures, and also on nanofluids, and then micro and nanofluidics. And then but initially I'll get started with the dip and nanolithography. So how does dip and nanolithography work? Well, turns out there is a very interesting multi-phase flows that happens on the nanoscale. The idea is to take a very sharp tip, which is, let's say, about 100 nanometers in diameter or 50 nanometers in diameter. So when you bring this very sharp tip, let's say this is about 5 microns high, and the tip radius over here is of the order of 10 to 50 nanometer, let's say. Now a very interesting thing happens, which is from the ambient humidity, water droplets start forming on the tip over here. Okay. So even though to begin with the tip is dry, because of the high surface energy, remember we talked about formation of this ice layer because of Lennard-Jones potential. So there is a little bit of a controversy in the literature. Some people say there is actually a ice layer on the tip of this sharp tip over here. And so typically atomic force microscope is used. The way an atomic force microscope works is you make a sharp pyramid, a pyramid with a very sharp tip, and the pyramid is of the order of about 5 microns high, and the tip radius is of the order of 10 to 50 nanometers. But because of this high surface energy of this tip, it tends to nucleate this semi-solid layer on the tip of this AFM probe. Okay. So there is one school of thought that says that when this water from the ambient humidity, when it coalesces on the tip, it forms a liquid meniscus. But there is another group that says that no, it's actually ice, according to what Lennard-Jones potential is predicting. But then when you put even a small amount of force on that ice, the pressure comes out to of the order of megapascals to gigapascals. And so what happens when you put pressure on ice? It melts, right? So one school of thought says that to begin with there is ice, but even if you put like 1 micronewton of force and you divide it by 10 to the power minus 9 meter square, that micronewton becomes megapascals or gigapascals, right? Because that small force over a large area translates to a huge amount of pressure. And what is pressure on the nanoscale? That itself is a very controversial topic. But in any case, so the other school of thought thinks that the ice melts, and so the advantage is if I coat it with an ink, any particular material, that material will dissolve in this meniscus, and it will, and as I drag the probe on the surface, I can write on the surface. Except since my tip is 10 to 50 nanometers in diameter, I'm going to be writing very thin lines. And not only that, I can make single molecule deposition. Okay. So what I'm depositing over here is, under certain circumstances, you can make 1 molecule thick deposition over here. Okay. So here is an animation taken from my former employer, NanoInk's website, that kind of demonstrates how this process works, this nanolithography process. So typically you do it on an atomic force microscope, and in an atomic force microscope or a scanning probe microscope, you have a cantilever which is about 20 microns wide, it is about 100 microns long, the pyramid is about 5 microns high, the tip is about 50 nanometers in radius, and then you can, instead of writing with one pen, you can write with multiple pens like a plotter, and then you can increase the speed of manufacturing of your platform. Okay, that is the whole idea. So, this is a multi-pen configuration that is writing the Nano Ink logo. So, this is an animation, a cartoon, right, but this image over here that you see is actual real image, which is this is a gold layer, gold surface, gold coated silicon substrate, and on top of that they use this ink called mercaptohexadecanoic acid. Okay, hexadecanoic means it is a carbon hydrogen chain with 16 carbons in it, hexadecanoic, essentially that is 16, and mercapto means there is a sulfur group at the end of this hydrocarbon. Okay, and so when you try to write with this pen, with this ink, that sulfur binds with the gold, okay, by chemical bonding, and that gives you a 1 molecule thick deposition on the surface. Right. Now, the big question is, okay, I can do this, what is the big deal, right. So, I can write, and so the line width, if you notice at the very end of this movie, the line width is of the order of about 50 nanometers, okay, 50 to 60 nanometers. So, now I can make 50 to 60 nanometer lines which are only 1 molecule thick. Okay. So, the big question is, what can I do with it? Okay. So, people have envisioned lot of applications, making circuits that are composed of single molecules that gives you very high sensitivity and speed, to nanocrystals. We made a big breakthrough in terms of imprinting catalysts, and I am going to talk about it. You can also make high density gene chips and protein chips for diagnostics of diseases from, let us say, blood samples. You can make micro and nanofluidic devices. The other breakthrough we had in our lab was in terms of making sensors, okay, very tiny sensors that are very sensitive. But the biggest blockbuster application is actually in cryptography, and nobody really talks about it because everybody wants it to be secret. Okay. So, there is a lot of counterfeiting of drugs that happen, you get a lot of garbage drugs that are sold in the market, right, and particularly for high end drugs which are, let us say, about 10,000 rupees a piece, particularly for cancer therapy, for example. Those are the drugs that tend to get counterfeited a lot, and so the pharmaceutical companies, for example, are interested in finding out where in the supply chain is the bad pharmaceuticals coming in, okay, in the market. And so, one way to do it is to tag each of your capsules with tiny imprints, and because they are so small, normally people wouldn't know that they are there, and only the person who is putting that imprint knows where it is. And so, what they do is then they go to the market at different stages in the supply chain, they go and check which of the capsules have the tag on them and which of the capsules do not, and so from that they can figure out where in the supply chain the bad drugs are coming in. Okay. So, that is one example. There are a bunch of other ways, but nobody talks about it, and this scanning probe lithography is one way of preventing counterfeiting of drugs, but nobody publishes, nobody files a patent, they all want to keep it a trade secret. But this actually happens to be a big blockbuster application of this type of technology. But at the heart of it, if you think about it, is actually multi-phase flows on the nanoscale, okay, with a big commercial implication essentially. And of course, there is a bigger implication for solid state nanoresists. You can make microelectronic circuits by etching that gold and making now gold circuits on the. So, you can imprint your circuit on a gold surface, and wherever this ink has stuck, it provides a passivation layer, and then if you dip it into a gold etching acid, it will etch away the rest of the gold and you will have just the gold circuit remaining. Okay. So, that is the solid state nanoresist application. That happens to be a very attractive application for this technology. Now, the big applications we did was we developed a sensor for detecting explosives, okay, particularly for example, let us say you can put it in a oil refinery. So, if your critical gas concentration, your hydrocarbon concentration in the ambient, if it exceeds a certain value, you can shut everything down before an explosion happens, for example. Or you can think of defense applications where people could be leaving explosive materials, and so this could be a very effective way to detect explosives essentially. And the other application where we had a big breakthrough was in nano imprinted catalysts, where we deposited catalyst particles on a surface and we could grow carbon nanotubes or graphene at very low temperatures, and that revolutionizes the whole manufacturing paradigm for these type of nanoparticles. So let's look at how this nanoscale multiphase flows can be used for micro and nano manufacturing. Okay. So just as an overview, as I mentioned on Monday, let's see. Okay, I think my slides got reordered a little bit. Let me. Let's give it a second, it's trying to auto save the file. So So the first application is in life technologies, in life sciences. So one of the early projects I worked on while I was working at Nano Inc. Is the concept of what is known as ink wells. So the idea was, instead of having all of those pens write with the same color, can we make each of these pens write with different colors? Okay. So one of the concepts I worked on was this concept we called ink wells. The idea was to have capillary flow, pump inks of different color from a big reservoir up here into these tiny wells over here. These wells are of the order of about 10 microns in diameter. Okay, and this channel that you see is of the order of 5 microns in width. Okay, so you can use a capillary or wicking mechanism to let the ink flow into each of these small wells that you see, and these wells have the same pitch as the pitch of the tips on this cantilever. So you could go dip your tip, and each of these tips will have different colors, and then go and write. Okay, that was the whole idea. So then the next challenge was, can we make each of these pens write separately? So right now the configuration, I'll write red, green, blue, yellow all at the same time. But the next idea is, can I make each of these write at different times? I can write red when I want it, I can write green when I want it, and so on. So we came up with the concept of a thermal bimorph, and there is a chance this video may not work, but the whole idea is to make this cantilever a thermal bimorph. So you have a silicon nitride cantilever, and then on top of the silicon nitride cantilever we deposited a layer of gold. So now it has become a bimorph. When I heat it, the gold will expand more and the cantilever will go down, and when I take the heat away, the cantilever comes back to its original position. Okay, so to do that, there is a micro heater at the base of this cantilever that heats it, and then when you take the current away, it just cools down on its own. Okay, so using that technique, we were able to write different colors at different times. So the next concept was, after I joined Texas A&M, then it came to my mind that you could use this cantilever platform, this bimorph cantilever, as a calorimeter. Okay, what does a calorimeter do? It measures the temperature at which a particular chemical reaction happens, whether it's oxidation or some kind of chemical degradation, and then what is the enthalpy of the reaction, right? So the idea here was, well, I have a cantilever, I have the gold layer on top of it, I have the micro heater at the base, and this is how it looks like under a microscope. In essence, you have an array of these, with each of these having a heater at the base of the cantilever, right? So the idea was, if I shine a laser light on it, and then I look at the reflection of the laser on a screen, okay, and then if there are 8 of these, and this pencil laser that I am using, a pencil laser like this will do the job, because within about a millimeter there are 8 of these guys, of these cantilevers, right. So, when I shine a laser on it, I will get 8 separate reflections from 8 of these gold coatings, okay. And then when I heat it up, each of these cantilevers are going to bend, and the reflected ray that I see on the screen, on the projection screen, is also going to move up and down as the cantilevers move up and down. And so, you could use this principle for detecting a chemical reaction. How is that? Well, here is a solid model that shows you have your normal pencil laser, you have these 8 of these cantilevers here, and you are looking at the reflected ray. And instead of having a projection screen, I can have a photo detector that can detect each of these reflected spots. And then the idea is, if each of these cantilevers are at a different temperature, let us say one is at 100, the other is at 200, the next is at 300. Okay. When I am in pure air, they will each deflect by a certain angle, because each of them have a different current, and therefore different amounts of heating, and therefore different amounts of bending, right. Now, if I expose this to some sort of a vapor that starts combusting, okay, the heat of combustion that will be released will heat up the cantilevers even more, isn't it. So, they will bend even more, but not all of the cantilevers are going to bend. Only the cantilevers that are above the ignition point will bend. So, let us say the ignition point is 300. So, the cantilever at 100 and 200 will not bend as much, but the cantilever at 300 and higher, they will all bend by a big margin, because now there is a catalytic combustion happening on the gold surface, and therefore, the temperature will increase, and once the temperature increases, those spots will move by different margins. So, the difference between the deflection you see in pure air and the deflection once you expose it to a combustible vapor, that difference is proportional to multiple parameters. Okay. So, so in order for us to figure, and so in essence, this becomes a calorimeter then, because the cantilever that bends first, that 300 degrees Celsius, that tells you what the ignition temperature is, right, at what temperature the chemical reaction starts. And then the amount of bending that you get is proportional to the enthalpy of the reaction. So, therefore, by monitoring the amount of bending, you can monitor the enthalpy of that particular reaction. So, now you have made a very tiny miniaturized calorimeter, a nanocalorimeter, that can act as a nano nose. It can sniff around, and it can figure out what kind of material or vapor is coming into the room or in a particular area, right. And you can build the intelligence into the chip itself. So, then it can correlate and say, okay, this ignition temperature, this enthalpy, it is probably this class of explosive material, for example. Okay. So, we did some analytical modeling. So, we did the model for how much the cantilever, the bimorph, will bend if you heat it up in air, and so we were able to predict the amount of bending that we will get, and these models are out there in the literature. There is nothing novel about it. Okay. And then what we did was, we did the same calculation when we are exposing it to a pure combustible material like acetone, and our prediction said that if you expose this to acetone vapor, the bending will be higher than when you expose it to an alcohol vapor, the bending will be lower. Okay. And so, based on that prediction, we did our experiments, and we found that the predictions were pretty consistent essentially. So, we could measure pure combustible materials like acetone and alcohol, and then we did some experiments with gasoline, your petrol, and we saw that we could detect petrol as well. Okay. And then one of our collaborators said, can you detect chemical warfare agents like mustard gas, okay, like the ones that are happening in Middle East right now. And so, of course, we are not certified to handle mustard gas, you need a certified facility to do that, but there are mustard gas simulants that are available commercially, and their chemical properties are pretty nasty. So, we did the experiments on a very limited basis, and we showed that we could detect even mustard gas simulants, what are known as CEES or half mustard gas. So, that shows the feasibility of using this platform for detecting both combustible materials, explosive materials, as well as chemical warfare agents. Okay. The next breakthrough we had in our lab was around the time we were doing all these projects, we also had a grant from DARPA, a small seedling project, where we were trying to make carbon nanotubes using dip and nanolithography process. Okay. The idea was you deposit catalysts, and then you put it into an oven, and if you expose it to methane or ethane or acetylene, wherever the catalyst is, it finds the catalyst and grows into a carbon nanotube. That was the whole idea. And so while we were doing the project, I came across this review article in Materials Today, and they said that carbon nanotubes have been around what, 20, 30 years. Do you see a computer chip that has carbon nanotubes in it yet? None, right? And they are saying carbon nanotubes have even better properties than metals, right? And they are this wonderful pixie dust that does a bunch of different things. But yet there is you are yet to see a single nanoelectronic product that has carbon nanotubes in it. Okay? And so the reason is, even though they have very wonderful properties, their manufacturing protocol is pretty nasty. Okay? And so that's why you don't see a lot of incorporation of these materials in modern technology, because processing them is actually a very difficult task. Okay? And so they identified 4 different bottlenecks that's preventing the use of carbon nanotubes in nanoelectronics. Okay? So the first bottleneck they identified was the ability to grow carbon nanotubes exactly where you want it. Okay? It's not very easy to do that. It's kind of like implanting a hair in your head, on a bald head, and wanting a hair exactly where you want it, right? And then the second thing is, you want to have carbon nanotubes have different types of properties. You have semiconducting nanotubes and you have conducting nanotubes. So you want the conducting nanotubes that communicates between your chip and your electrical connection in the via. Okay? And you want the semiconducting nanotube as a diode, wherever your computation layer is, where your device layer is. So you should be able to grow carbon nanotubes that are conducting in the vias, and then semiconducting nanotubes where the device layer is. Okay? And so that was the second bottleneck they identified. The third bottleneck they identified was, you need a certain density of carbon nanotubes. You want 100 of these in 1 micron square. Okay? But the fourth bottleneck they identified, which is the most difficult one, which is to grow carbon nanotubes at temperature less than 300 degrees Celsius. Normally the way carbon nanotubes are made is, you take a substrate on which you want carbon nanotubes, you coat it with iron to about 20 nanometers thick, you put it into a furnace at 800 degrees Celsius, you pump acetylene, and the acetylene becomes carbon nanotube on that iron layer. Okay? But your electronic chips, they don't survive, the processing conditions cannot exceed 300. So there is your bottleneck. I have made the rest of the chip, now I want to make a carbon nanotube on it, but now I have to put it into a furnace at 800, and that's going to destroy everything I have made so far. So there is a desperate need to make carbon nanotubes at 300 degrees Celsius or below, or even graphene, which is supposed to have even better properties than carbon nanotubes. Even graphene needs a temperature in the range of 600 to 800 degrees Celsius for fabrication. So even if you were to make a electronic chip with graphene in it, your processing temperature needs to be less than 300. And it so happens, when this review article came out, around the same time we had actually solved all 4 problems. Okay? So let me show you how, except that we were not aware that these are the implications of what we were doing, talking about convergence, right? So you can see there are so many different disciplines that are coming together, and each of them are affecting each other essentially. So our initial plan was to take a sharp tip, dip it into a salt solution like lichen chloride or palladium chloride, and then go and deposit these small particles, these droplets, on the surface using the DPN process. So now I have single molecule thick, or maybe 10 or 20 nanometer thick layers of this salt, okay, nickel chloride or palladium chloride. And then we were sending it to there is a NASA lab called JPL, Jet Propulsion Lab. So my collaborator at that time was Dr. Anupama Kaul. So she had a very nice carbon nanotube furnace in her lab. So we were sending it to her, she would put it into the carbon nanotube furnace, PECVD furnace, plasma enhanced chemical vapor deposition. And after this thing came out of the furnace, we could see, actually it's not very clear in this picture here, but you can see here there is a very nice carbon nanotube that grew, vertical carbon nanotube that grew on the surface. So we have the ability to grow carbon nanotubes exactly where we want it. Okay? And then DARPA came back to us and said, we don't want the carbon nanotube on the substrate, we are using this tip with the meniscus to deposit the material, right? So they said we want the carbon nanotube on the tip. Okay. So, we scratched our head and we said, well, maybe we will give it a try. All right. So, what we did next was we took this scanning probe tip, we dipped it into a inkwell. You can see there is a well here, there is a well here, there is a well here. So, we would pump, let us say nickel chloride or palladium chloride, into this well by capillary pumping, and then go and take the tip and dip into that. Okay. Now, my tip is coated with the catalyst particle, palladium, nickel, and so on. And then what I would do is I will take another inkwell like this, make a solution of graphene or some kind of carbon, okay, and again dip the tip. So, now I have both the carbon and the catalyst, because those are the two things I need to make the carbon nanotube. And then because this scanning probe had a heater at the base, we would crank up the temperature, current, so that the heater would heat up to a very high temperature and then fail. Okay. And normally, because this is gold and silicon they form a sort of a composite called gold silicide, and that happens about 300 degrees Celsius. And so, we know our heater for sure fails at 300, because at 300 degrees Celsius it forms the gold silicide, and once it forms the gold silicide, the heater becomes non-conducting and the whole thing fails at that point. Okay. So, we know for sure that the system temperature never exceeded 300 degrees Celsius. Okay. So, after we did the heating of the tips, we went back and looked at it under a electron microscope. So, this is the cantilever, that is a pyramid, that is the tip of the pyramid, and we could see this wire like things have formed on the surface of this tip. So, now we are able to grow nanotubes on the tip, but the question is what kind of nanotube is it. Okay. So, we did a Raman spectra, and typically in a Raman spectra there are two things you look at. Okay. One is what is known as a radial breathing mode, where this is the wavelength of the spectrum and this is the intensity, and typically up to 300 per centimeter wave number is your radial breathing mode, because if you think of a nanotube as a sort of a steel tube, for example. Now, the tube can vibrate longitudinally, right, or it could vibrate along the radius, like when we breathe in, our the windpipe expands, and then we breathe out, the windpipe contracts. So, the carbon nanotube also oscillates in that radial breathing mode. Radially it goes out and then shrinks, you can have that mode of vibration, right. So, the radial breathing mode tells you what type of carbon nanotube it is. Okay. And so, if you divide the peaks in the radial breathing mode by 300, that tells you the diameter of the carbon nanotube. So, I see there is a, I am sorry, by 250. So, I see there is a peak at 253. So, if I divide it by 250, that tells me I have a carbon nanotube of 1 nanometer diameter, right. So, similarly, if I divide 160 by 250, I know I have a carbon nanotube of about 0.8 nanometer diameter. Okay. And then you look at what is known as the defect band and the graphitic band. Okay. So, because at the end of the day a carbon nanotube is nothing but graphite, a graphite sheet rolled into a nanotube, right. It is like taking a paper, a sheet of graphite paper and making a tube out of it. And so, this graphitic peak comes because you have those hexagonal structures of carbon in graphite, and if you have any defect in the carbon nanotube, if there is any lattice defects, a carbon is missing or a carbon is distorted and so on, that appears in the D band, the defect band. And if your defect band is smaller, the peak is smaller than the graphitic band, then it is a single walled nanotube. Okay. So, this shows that we were getting single walled nanotube at temperatures less than 300 degrees Celsius, okay, all coming from multiphase flows. Okay. Now, the next challenge that we got from DARPA was, well, you are using electrical heating, can you do the heating using laser? So, we went to a Navy lab called SPAVAR or System Center or SSC, this is in San Diego, and they have this type of laser known as Excimer laser, and they have different wavelengths of laser that you can use. Okay. So, we went there. So, this is where the source of the light comes in and hits the chip and heats up the chip over here. Okay. So, we put our silicon chip with a coating of fullerene and palladium chloride and nickel chloride in there, and we heated it up thinking we will get carbon nanotubes. We ended up getting these flowers. You can see this flowers type of structure that has formed. I think in the TV it's more clear, you can see those, you know, a sort of a flower with petals type of structure that has formed. So we were expecting to get carbon nanotubes, we ended up with graphene, and here we took a IR camera and we measured the temperature of that substrate, and we knew from the IR camera measurement that the substrate temperature never went above 120 degrees Celsius. Okay. So now we have a procedure to make both carbon nanotubes and graphene under room temperature conditions, because we are only heating up at localized spots and we are getting carbon nanotubes and graphene. So now the big question is, why did graphene form and not carbon nanotubes? Okay. So we do not have a definitive answer for it, but my way of explaining it is this was actually a carbon nanotube. Okay. It grew up as a multi-watt nanotube from the catalyst particles that we deposited, but then the Excimer laser has a very high energy. So what it did was, then it went and chopped up the carbon-carbon bonds. So you can think, if I have a tube which is highly stressed, and then I go and take a scissor and I cut it up, what will happen? Because of the stress, it will open up like a flower. So I think that's what happened over here. Okay. So Navy actually filed a patent, they got it within like 2 years of our, no, actually within, I think 3 years of filing the patent we got it, which is very exceptional. Normally it takes about 4 to 5 years to get a patent application approved. So so we got a patent out of this that shows that you can grow carbon nanotubes exactly where you want it. Okay. You can grow it at a very low temperature, you can grow it at a very high density, but the last part was the ability to grow carbon nanotubes of conducting type or the semiconducting type, right. So we had one experiment which we could not repeat, but there was one experiment we could show that you can control the, we could get carbon nanotubes of one single chirality, you know, which was a conducting nanotube. So we still do not know what was the proper conditions of the experimental you know, apparatus that gave us that one single carbon nanotube of one single conductivity, but it shows the feasibility that it is possible to make carbon nanotubes of different conductivities, you know, with controlled you know, manufacturing essentially. So that's as far as, you know, application to microscale and nanoscale manufacturing of multiphase flows is. Okay. So the next thing I wanted to talk about was in terms of boiling and condensation. So let's see how we are doing. We have about 15 minutes. Okay. So let's talk about the boiling part first. Okay. So I am going to repeat myself a little bit over here. We went over this slide on Monday, right. So I am going to just refresh your memory and talk about it one more time. So you know, as I mentioned on Monday, we were taking these cooling oils that are used for cooling the avionics chips in an aircraft, particularly the chips that control the radar of an aircraft, for example. They tend to have very high power rating, and so they dissipate a lot of heat, and so typically you cannot use water to cool them because water can cause, you know, electrolysis and fire. So they use a type of coolant called PAO, polyalpha olefin. It's an oil, but it looks like water. When you put it in a bucket, you won't be able to distinguish between PAO and water, they look almost the same, except that this one has a little slightly different density and viscosity than water. And so what we were doing was we were taking this polyalpha olefin oil and we were mixing it with nanoparticles or forming nanofluids, and oil has a heat capacity of 2 joules per gram Kelvin, water has a heat capacity of 1 joule per gram Kelvin. I mix the two together, I expect it to be less than 2, but the answer came out 2.5. Okay. So the heat capacity jumped by anywhere between 20 and 50%. So next summer we went back to Air Force Research Lab, this time we put carbon nanotubes and the heat capacity enhancement was even higher. Okay. And so at that time we did not really understand what was the mechanism by which the heat capacity was going up, but we pitched an idea to Department of Energy, the Solar Energy Technology program, and we said that, you know, they use these salts called solar salts to store the heat from a solar thermal, you know, power plant. Okay. And we said, well, the molten salts have very bad thermal properties, maybe by putting nanoparticles in it you can improve the heat capacity and the thermal conductivity. Okay. So DOE gave us a grant and we put nanoparticles or different types of nanoparticles, and at this point we had a better understanding of where the enhancement was coming from, and so we were able to enhance the heat capacity anywhere between 20 to 120% in a very repeatable manner. We could repeat the experiments this time and show that it's a repeatable synthesis protocol. So around the same time we were also doing pool boiling and flow boiling result. So we got some grants from NSF and Navy where we were doing pool boiling experiments using a refrigerant, and we made carbon nanotube coatings, and the critical heat flux went up by 60%. The heat flux at Leidenfrost point went up by 300%. Okay, and to us it seemed logical. Well, you are putting carbon nanotubes in there. Nanotubes have a very high thermal conductivity, so maybe it was enhancing the efficiency of the heater in conducting the heat into the fluid. So to test this hypothesis, we, instead of using carbon nanotubes, we decided to use silicon fins, nano fins. Okay, and silicon has a lower thermal conductivity than carbon, and we were expecting the amount of enhancement we would see in the CHF would be lower in carbon, lower in silicon. And then to our horror, we found the CHF went up by 120%, just double of carbon nanotubes. It didn't make sense because silicon has a lower thermal conductivity. Around the same time, we were also doing some flow boiling experiments, where instead of doing pool boiling, we were flowing it in a chamber. And sure enough, the flow boiling heat transfer also went up by a factor of about 2. Okay, we got enhanced by about 180%, more like a factor of 3 essentially. We also did some experiments where we made carbon nanotube coatings in a condenser, a microchannel condenser, and once again the condensation heat transfer heat flux jumped by about 100%. And then in parallel we were doing some spray cooling experiments a few years later, where we used titanium nanoparticle coatings, and the heat transfer the heat flux went up by a factor of 6 to 8, or more like 7 to 9. Okay. So now the big question is, where is this enhancement coming from, number one, and why is the enhancement so lopsided? Why is it so distorted that your lower thermal conductivity material is giving you a higher enhancement? Okay. So we wanted to answer those questions. In any case, so as I mentioned on Monday, to explain it, we call it this Nano Fin Effect, where we find that the parameters at the interface between the solid and the liquid are the ones that are dominating the game. And our understanding of what is happening at that interface between the solid and the liquid is there are 3 thermal impedances. Okay, so there is a resistor, there is a capacitor, and then there is a diode. So my presentation today is going to be focused on estimating what is the magnitude of this resistance, what is the magnitude of this capacitance, what is the magnitude of this diode. You all with me on this? Okay. So that's what we are going to explore as a part of our lecture today. Okay. And where do they come from? That's the other part as well. So as I mentioned, on Monday, the last 12-13 years of research, what has that yielded in terms of impact and convergence? Well, of course, it has yielded a book, because 70% of Navdeep's thesis is this book basically. We also have a distance learning course that is being marketed by ASME called Nano Coatings for Enhanced Thermal Engineering, and then of course one of my former students started a company to commercialize this technology, and the business plan that he came up with won a few awards at different business pitch competitions, particularly the Texas New Ventures competition essentially. And so this particular company is focused on these additives. It's not even nanoparticles. You put these additives like salt or soap, and when you heat it up, it generates nanoparticles on demand. And what we find that these nanoparticles, not only do they enhance the cooling and the thermal storage, heat capacity and thermal conductivity, but they also enhance the corrosion resistance, and the corrosion goes down by a factor of 2, which is actually a big deal for heat exchangers, because heat exchangers have a lot of fouling and corrosion issues that these additives can take care of. Okay. So that has been the outcome of this research. So now let's take a step back and let's look at all the different types of industries out there that need some kind of heating or cooling. okay, particularly cooling. Heating is not that much of a bottleneck, it is a cooling which is a more sophisticated problem, right. So, if you look at cooling applications, things like solar panels or your nuclear or propulsion or rocket nozzle, you are looking at heat fluxes of the order of 100 watts per centimeter square. But if you look at missile engines or some of the high end laser diodes, for example, you are looking at cooling needs that are going to be about a kilowatts per centimeter square. Okay. Now, I have this problem. What do I have in my toolbox to solve this problem, right? So, if I go back and if I look at simple convecting cooling using air or liquids, I can go only up to about 0.1 watts per centimeter square. Okay, but I have to get to kilowatts. That is what I need. Okay, the next option is to use things like forced convection instead of using natural convection. Use some kind of pipe or microchannel and use either a refrigerant or a water based coolant, but that can only take you up to a watt per centimeter square. Okay. And then if I look at boiling, technically your fluorocarbons can give you about 10 watts per centimeter square. If you are boiling water, you can, well, under some circumstances the CHF can go up to about 100 watts per centimeter square, but the big need is in kilowatts. Okay, so I got to enhance the performance. So, boiling looks like the only option for that kind of cooling applications, isn't it? And so, I need to somehow enhance the performance of boiling. Okay, so, that is the basic problem. I need to extend my boiling critical heat flux from the current technology of 100 watts per centimeter square to kilowatts per centimeter square. So, that justifies boiling research. Okay. So, now let us look at this video that I showed to you yesterday. I hope it works once again. Oops. Let me play it from the player itself. Okay, so, we discussed this already on Wednesday. So, what you see is a vapor bubble that is growing. This is the heater substrate, and remember I plotted those delta functions. So, wherever my liquid vapor interface touches the surface, or in film boiling wherever that vapor film thickness is the lowest, that is where I get the maximum heat transfer, and the point at where I get the maximum heat flux, that is where the cooling occurs. Right, it is kind of like taking a table, and let us say I have heated the table uniformly to 100 degrees Celsius, and then I take a jet of air and I heat it at one point. So, wherever the jet of air is hitting the table, I get a peak in the cooling, I get a peak in the heat transfer, and wherever there is a peak in the heat transfer, there is a cold spot, isn't it. So, it is kind of like that, except here you have rapid vaporization of the liquid. And so, like a rocket nozzle, it is dumping a vapor jet on that surface, okay, and in the process it is cooling the surface, and the liquid is getting vaporized and ejected off like a rocket, isn't it. That is how it is all working. And so the location at which I have a peak in the heat transfer, particularly at the point of minimum vapor film thickness or wherever this solid liquid vapor interface happens. So, that is where I am getting a peak in the heat transfer, and therefore, the temperature is lower and it is plotted in blue. So, you can see this is about 200, this is about 220, okay, and the dimension of that cold spot is only about 15 microns in width, and it is only about 15 microns thick. So, it is kind of like a toroid that goes under the bubble, okay, a very tiny width and a very tiny thickness, but that is where about 60 to 90% of your total heat transfer is happening. Rest of the surface is virtually, you can treat it as insulated, and you would not make a calculation error by a big margin, because bulk of that heat transfer is through that cold spot. Okay. So, and then we looked at our model, we made a copper heater versus a steel heater, and what we found was in the copper heater the width of that cold spot was almost double. Okay. The reason is copper has a higher thermal diffusivity or thermal conductivity, so it tends to give you a bigger temperature spread, versus in steel has a lower thermal conductivity and lower diffusivity, so that cold spot is thinner. Okay. What does that mean? For the same average temperature for both the copper heater and the steel heater, copper always gives me a higher boiling heat transfer. Okay. Now, all the correlations that we have covered in this Gyan course, none of them account for the thermal conductivity of the heater, but we know from our experiments that a heater with a higher thermal conductivity will give you a higher vapor production, even though the average temperature is still the same. Okay. And the reason it happens is because of this cold spot phenomenon. Now, since 1960s, people had theorized that there is a cold spot, okay, but nobody could model it to begin with, all right, because people would assume a certain static shape for a bubble and do the analysis, and number two, nobody could measure it. Okay. At least now I have a model that predicts, starting from a simple Rayleigh-Taylor instability. We start with a simple configuration of a vapor layer with a liquid layer on top, and let the computer program figure out the Taylor instability and figure out those oscillations of the vapor bubble. Okay. So, it starts, if you notice, it starts in the beginning with just a simple vapor film thickness, and the whole thing develops on its own without making any assumption for shape. So, now I have a model where I do not make any, see, it starts from a simple vapor configuration and then it grows on its own. You know, we are not imposing any shape on the bubble is choosing the shape based on the Navier-Stokes equation and how the pressure field evolves with time. Okay. So, this is the first time in the literature that we could show how a cold spot forms, and that the cold spot forms on the outer edge of the bubble and it moves inner radially with time. Okay. So, but then the other big enigma is, can we go and measure this cold spot? Okay. So, I graduated from UCLA, went to work in the industry, but at the back of my mind I kept thinking, how do I measure this temperature, because it is very tiny. It is only about 50 microns in width and 50 microns in thickness. I cannot put a 1 millimeter diameter thermocouple in there, because that itself will serve as a nucleation spot and disrupt the whole boiling process. Normally people put a thermocouple in the heater about a millimeter below the surface. To begin with, it is a 1 millimeter heater, 1 millimeter thermocouple, and it is a millimeter below the surface, but all that fluctuations in temperature is occurring within the first 50 microns or 100 microns of the surface. So, a big thermocouple way below will not be able to see it, right. But more fundamental than that, the question is, my results are showing that the higher the thermal conductivity or diffusivity of the heater, the wider the cold spot, right, and higher the the total boiling heat flux. So, if I can come up with a material that has even higher thermal conductivity or diffusivity than copper, then I can get even higher heat fluxes. Okay. And then I looked at the literature, and all these physics papers were coming out, and they were saying, oh, carbon nanotubes have very high thermal conductivity, almost 10 times that of copper. Okay. So, then we said, okay, maybe carbon nanotube will even give us a bigger cold spot. That was the process of thinking why we decided to use carbon nanotube. So, that answers the why nano question. Remember this why nano question that is there. So, that is how we justified that carbon nanotubes can give us higher heat transfer, not because it was in fashion or because the funding agencies were giving money, but because we had a formal physical justification to show that carbon nanotubes should give you enhancement. Okay. So, that justifies the why nano question, and as I mentioned, we also decided to use these. So, the philosophical discussion that we were having was with respect to this cold spot and how we go about detecting it, right. So, to begin with, the first problem that we were thinking of was how do we enhance this cold spot. Either we increase the width of this cold spot, because it is a delta function, right. So, the wider the delta function, more heat flux I have, or the other option is I can increase the number of cold spots by making smaller bubbles, but more number of bubbles. Okay. Now, if you think about the time period of a bubble, it is roughly 100 millisecond. You are looking at a frequency roughly of the order of 10 hertz, is not it? But out of that 100 millisecond, about 50 millisecond is the waiting time. If it is fin boiling, there is a alternate departure of the bubbles, right. So, half of the cycle the bubble is sitting there, and then the other half of the cycle it is growing in fin boiling. Now, when it comes to nucleate boiling, you roughly have about the same time period, but in nucleate boiling your bubbles are smaller. Okay. And then the other part is in nucleate boiling, about half of that 100 millisecond is what is known as the waiting time before the bubble nucleates. Okay. And then after the bubble nucleates, it grows and departs, and that happens in the next 50 millisecond. So, in other words, if I look at the frequency of this cold spot, when I see it forming on the surface, I expect it to be somewhere between 10 and 20 hertz. It should be somewhere in between that. Does that make sense? Okay. So, I did my PhD thesis, I proved that there is a cold spot. Now, I have a model that operates from first principles, that shows how the cold spot form, how they move inwards, radially inwards as the bubble grows and departs, right. So, at the back of my mind, I kept thinking I got to measure that temperature. And so, the first idea that came to mind was that of a nano thermocouple, a thermocouple that is so thin that it does not affect the temperature transients around it. Okay. So, and then the other part was, okay, what other heater material is out there that has higher thermal diffusivity, and of course, carbon nanotubes have very high thermal diffusivity. So, we decided to use carbon nanotubes. Okay. Now, then we ended with all these weird results. So, to resolve it, we had to resort to molecular simulations, and while we were doing the measurements using these nano thermocouples, we found that there was a lot of fractal type of shapes that was happening on the heater surface. By fractal I mean self repeating structures, right. So, just like in condensation I showed, you could have a big droplet surrounded by small droplets surrounded by smaller droplets. You would have a very similar configuration in boiling under certain circumstances. And normally, if a system is fractal, it exhibits what is known as chaotic behavior. By chaotic behavior, as I mentioned, it is like a pendulum. Let us say I have a pendulum which has a time constant of 1 second, but it never reaches 1 second. It oscillates about 1 second, but it never gives you 1 second, right. That is a chaotic behavior, where a system circles around a particular pole, but never really reaches that pole. Okay. So, that is one of the elements of chaos theory, where a system kind of repeats itself, but it does not have a fixed periodicity. The periodicity of that repeating structure changes from one cycle to another, and it is never exactly the same. Okay. So, all these things started happening around the same time, and it was kind of drinking from a fire hydrant, because so many things we were observing and we were trying to make a sense of it essentially. Okay. So, now what do I mean by the nano thermocouple? So, if I take a typical refrigerant vapor bubble, because these experiments that we were doing were using this refrigerant called PF5060, it also goes under another trade name called FC72, and it is supposed to be a substitute for Freon. Okay. Now, if I look at a typical vapor bubble, typical vapor bubble is about 700 microns in diameter. Okay. And so, that is your vapor bubble shape. Your typical bead thermocouple is bigger than your vapor bubble, it is about a millimeter in diameter. Okay. And then if I take a quarter of this bubble, that is how it will look like, about 350 microns radius, and we decided to make nano thermocouples which are about 100 to 200 nanometers thick and about 200 microns in width. And our thought process was something like this should not affect a bubble this size, and later on we found that we had made a mistaken assumption. Okay, we will see as we look at the results. All right. So, next thing is we wanted to make these nano thermocouples. So, we made a nano thermocouple. What is a thermocouple composed of? If I am using a K type thermocouple, I have a chromel wire, okay, and what else do I have? Alumel wire. Okay. Chromel is I think about I think 90% nickel, 10% chromium. Alumel is about 70% nickel. There is I think 10% aluminum and a bunch of other things. Okay. So, the junction of these two alloys gives you the temperature sensor. Okay. So, what we did was we deposited a thin layer of metal of chromel, then we deposited a thin layer of alumel, and wherever they join in the center, that is where we are measuring the temperature. And we made an array of these thermocouples of like 3 by 3 or 5 by 5. So, we could have 9 or 25 measurements in one go in about a millimeter by millimeter square area. So, we could measure temperature with very high spatial density, okay, because we had these tiny tips which were only about 100 200 nanometers thick, 200 microns wide, and in an area we could measure with very high density. Now, what is the speed of this thermocouple? How, what is, what fluctuation of temperature can we detect? So, this is looking under a microscope, wherever these square things that you see are the bond pads, that is where we soldered the wire. Okay. So, we take some silver paint and we soldered the wire in there on that bond pad. What you see is that square pads over here, these square pads, this is where we bond our wire. So, we can dump it to the data acquisition systems for recording the temperature. Does it make sense? Okay. So, we made the nano thermocouples and and bond the wire, and this is how it looks like under the microscope. This is actually a 5 by 5 array. We are measuring 25 temperatures. You can see there are so many bond pads, right. So, we can measure 25 temperatures within like a 1 millimeter or 2 millimeter square area using this technique. And so, if you look at the speed, we do a Fourier analysis. So, what is a Fourier analysis? Your L square divided by alpha is a time constant. What is L? It is volume divided by surface area, right. So, if I look at the characteristic length, volume divided by surface area of these thermocouples, the characteristic length is of the order of about 0.5 microns. I am sorry, yeah, about 0.5 microns. And since these are nickel alloys, the thermal diffusivity is similar to that of nickel. That is about 2.3 times 10 to the power minus 5 meters square per second. So, if I do a L square by alpha, if I take the square of this divided by this, I end up with a characteristic time constant of the order of 10 nanosecond, which means if I have a temperature that is fluctuating every 10 nanosecond, I will be able to measure it. Okay. So, we are limited more by the speed of the data acquisition system than by the speed of the sensor. Okay. So, our limiting case here is not the sensor resolution, it is the data acquisition capability. Okay. So, now we can measure temperature with very high spatial resolution and with very high temperature resolution. Okay. So, then we made, this is our boiling apparatus. This is a solid model that shows on the side. So, basically we have a copper heating block in which we have cartridge heaters, and then we put thermocouples in the copper heater to measure the temperature gradient in the copper heater. Okay. And then on top of the copper heater we put a silicon wafer and then we clamp it. Okay. And then we put it inside a viewing chamber. The connections for the electricity come from the bottom, the thermocouple wires go out from the bottom, and then we fill it with a refrigerant. Okay. That is what you see over here. Here is the viewing chamber, it is filled with a refrigerant, that is the height of the refrigerant layer. You can see there is a silicon wafer with the clamp, and you can see these wires that are bonded to the nano thermocouples. Okay. And then we do a boiling experiment. This is very close to critical heat flux, and I think Dr. Professor Das was mentioning yesterday that the bubbles tend to move in a particular direction, right. The reason is it sets up a natural convection current over here. Okay. You have a cold surface on the top, a hot surface in the bottom. So, wherever you do not have boiling, you have natural convection. And so, the way the natural convection rolls work is as they rotate, they tend to focus the bubbles to the center. And you can see the dimension of the bubbles close to critical heat flux. You can sort of see these vapor column sort of structures that are forming in the CHF. Okay. So, we could do the experiments at different temperatures, different wall superheats. Okay. And then we looked at the fast Fourier transform of this temperature fluctuation with respect to time. Okay. Towards the end of the lecture, I will come into the boiling chaos part of it, but those temperature fluctuation with respect to time have fractal structures in them. What do I mean? I have a big oscillation, and then top of that oscillation, if I resolve it, I will see some tiny oscillations, and if I resolve the tiny oscillations, I will see another tiny oscillation on that, and this is very characteristic of velocity fluctuations in turbulence. In turbulence also you get a very similar thing. You have a big vorticity, a big vortex that is rotating, or if you look into a river where there is a recirculation zone forming on a river, watch closely. Okay, you will see that there is a big vortex that is circulating in the river, and if you focus on it, you will see there are smaller vortices actually riding on that big vortex. They are rotating around with it, and then if you look at one of those smaller vortices, if you look closely enough, you will see they have even tinier vortices rolling around on it. Okay, so we have a similar thing with temperature like you have with velocity in turbulence. Okay, so if you measure the velocity fluctuation in turbulence at a particular location, the velocity fluctuation will give you the signatures for the big vortex, the middle vortex, the smaller vortex, and it all comes out in the velocity fluctuation measurement if your sensor is sensitive enough. Okay, and we are seeing similar things in temperature as well. So if time permits, I will get into the analysis of those fractal structures and chaos, but for now let us just look at a very simplistic image, and the simplistic image is what is my primary frequency of oscillation. Okay, and remember we had the discussion where I said that the primary frequency of oscillation should be somewhere between 10 hertz and 20 hertz, or somewhere between 10 and 25. Guess where the fluctuation is? Right around 15. Okay, so we can sense cold spots using these nano thermocouples. Nobody has been able to do this before. Okay, so nano thermocouples give you the opportunity to do it. All right, and not only that, we were discovering all these fractals and chaos because now our sensor is very sensitive, so it is able to pick up these finer temperature fluctuations that nobody else has picked up before. Okay, and it is all coming from those cold spots, right. So in other words, these cold spots that are forming on the bubble is not static. Okay, the bubble also wobbles, and just like in a vortex you have this the vortex rotating, so your temperature field is probably also rotating, and it is all not perfectly circle, because on that circle itself there is also another oscillation that is happening. So remember when we were talking about the cylindrical instability, we said that the droplet or that jet oscillates in the circumferential direction. So you probably have an oscillation in the temperature in the circumferential direction as well, that our CFD model is currently not capturing, because we used a axisymmetric CFD model. But if I were to do a full r theta z simulation and have the elements of instability in it, there is a good possibility I will see that oscillation along the circumference itself, and what I am measuring in my temperature is those oscillations as well. Does that make sense? Okay. So there are a lot of things happening at that scale that is currently undiscovered. Okay, but we can see we can sort of hear it, but we cannot see it right now. So we can indirectly perceive it, but we have not directly visualized it. So now that we know the cold spots, the next step is make a carbon nanotube coating, because carbon nanotubes have high thermal conductivity. That is what we thought, right. So we made our own carbon nanotube furnace. So if you remember in my acknowledgement slide, I acknowledge one, all the professors that I acknowledge there. There is one acknowledgement is for Dr. Shayan Sinha, and so Dr. Shayan Sinha also is a Kharagpur graduate. His father was the department head of mechanical engineering at IIT Kharagpur, Dr. GL Sinha. So Dr. Shayan Sinha is an expert in carbon nanotubes, and this is the beauty of having your batchmates also doing research, because when I decided I am going to do carbon nanotubes, all I did was I called him, and he came to my home, stayed with me for 1 week, went to my lab, helped me set up this whole carbon nanotube furnace, which would have taken me 6 months to do. Within a week, because he was there, we got it up and running. So to a large extent I credit him for this particular work. Okay. And so how does it work? Well, typically you use a box furnace where you have electrical heating elements on the top and bottom, and then there is a quartz tube that goes inside. Okay, and inside the quartz tube what we do is we take a silicon wafer for the size of the heater that we have. We select a wafer of that same size as a copper block. We put it into the carbon nanotube furnace. We coat it with iron first, and then we push it into this furnace and heat it up to about 600 to 800 degrees Celsius, and then from the opposite side we pass nitrogen. and make that whole atmosphere inert, because we do not want our iron to react with oxygen and rust at that high temperature, because once you go to that high temperature the iron will oxidize, and if it oxidizes then it will not be a catalyst anymore. Okay. So, we first make the atmosphere purely nitrogen atmosphere, then we heat it up to 800 degrees Celsius while the nitrogen is flowing, and then once it hits about 800 degrees we mix a little bit of acetylene with the nitrogen and flow it into the system. And at that high temperature the acetylene, wherever it finds the iron, it reacts to form a iron carbide, and then it saturates the iron with carbide, and then the carbide precipitates out, and as it is precipitating out of the catalyst of course remains pure, right. A catalyst never participates in the chemical reaction, and so as that catalyst, the carbide is precipitating out of the catalyst, it forms into a carbon nanotube, okay, and it grows at about a micron a minute. All right. So, what we did was we made carbon nanotubes of two different heights. One is about 10 microns and the other is about 25 microns. Okay. So, we published this in Journal of Heat Transfer in 2006, and my co-author on that paper is Ray Bauman at UT Dallas, because the first set of carbon nanotubes that we tested before we even invested the money into making our own carbon nanotubes, actually Ray gave it to me. He made the carbon nanotube coatings and gave it to our lab, and we did the testing. So, what we did was we initially, when we did the carbon nanotube coatings, we decided to make carbon nanotubes of two different heights. Okay. One was 10 microns and the other one was 25 microns. Now, there was a reason behind this madness. I did not arbitrarily choose these two numbers. Okay. It came based on the computational CFD simulations I was doing, okay, and it will become clear a little bit later. So, let us look at it. So, we did the experiments, and so these are carbon nanotubes. So, you can see these tiny hair like structures here, that is your carbon nanotube, that is your about a half a millimeter diameter droplet of water, and you can see it is highly hydrophobic, about 150 to 160 degrees contact angle. Okay. And with the refrigerant we were using, the contact angle was less than 10 degrees. It was highly wetting for the boiling fluid that we were using. So, this is our nano thermocouple, chromel and alumel, wherever they are joining, that is where I am measuring the temperature, and then rest of the surface is coated with carbon nanotubes. So, if I magnify it, this is my chromel, this is my alumel, and you can see there is carbon nanotube all the way up to this junction. If I magnify it here, you can see these hair like structures, those are the carbon nanotube coatings. Okay. So, with the nano thermocouple I am able to measure the heater surface temperature, and therefore, the wall superheat. Okay. And then in the copper block I have the thermal the thermocouples. So, based on the temperature gradient from the thermocouples I can measure the heat flux going into my heater surface, right. So, and then if I take pictures, this is how it looks like. This is the bare surface, bare silicon surface without any coatings. All right. This is nucleate boiling. This is 10 micron size height carbon nanotube in nucleate boiling, and you can see I am forming sometimes very big bubble structures where bubbles are merging. Okay. And then between 10 micron and 25 micron there is not much of a difference in terms of the boiling performance, okay, the bubble structures that I see. The interesting thing happens in fin boiling. In fin boiling the surface becomes like a mirror, because it has formed a vapor blanket, and the vapor reflects the light out that blanket. So, you can see the vapor blanket, it has started reflecting the light, and then if you compare the bubble sizes, in nucleate boiling you get much tinier bubbles, in film boiling you get much bigger bubbles, because they are Taylor instability apart, and their size is of the order of Taylor instability. So, you get very big bubbles essentially. Now, without coating I get a very nice smooth mirror surface. When I use 10 micron coating, the mirror surface is not disrupted. When I go to 25 micron coating, the mirror surface has gone. The whole vapor blanket has collapsed. Okay. So, this is a very good way to prevent film boiling from occurring, because if film boiling occurs, your nuclear power plant is melting down. So, if you have fuel rods on which you have this fin boiling happening and loss of coolant accident and the catastrophic failure of the power plant. One way to prevent it or reduce that probability is to coat it with nanotubes, because what that does, and not only just nanotubes that are thicker than the vapor film thickness. So, what my CFD model was telling me was I get the bubble with different thicknesses of the vapor bubble, right, that vapor blanket. So, at the point you have the minimum vapor film thickness, my computer model was predicting that it was about 15 microns thick. So, a 10 micron carbon nanotube is not able to puncture that 15 micron vapor blanket, but a 25 micron carbon nanotube is able to puncture it, form a direct bridge from the solid heater into the liquid refrigerant, bypassing the blanket. So, now the blanket prevents heat from getting transferred, but the nanotube serves as a bridge, overrides it and transfers the heat directly to the liquid. But for that, your thickness of your nanotube coating needs to exceed that critical size in order for it to be effective in film boiling. Okay? And we see it. So, in other words, the Leidenfrost point that occurs on the 25 micron is actually at a much higher superheat. Okay? And therefore, you get a much higher heat transfer at the Leidenfrost point when it comes to the 25 micron heater, right. And we see that in the boiling performance as well. Let us see. So, if I look at this graph, this is my bare silicon wafer without any carbon nanotube. This is my silicon wafer with carbon nanotube. The red is 25 microns, the black is 10 microns, and their CHF is about the same. The higher thickness probably gives you about 20% higher CHF, okay, marginally higher CHF. So, in other words, as I keep increasing the thickness of my carbon nanotube, I get higher and higher CHF, but the delta increase in CHF is not that significant, only about 10 to 20%. But the interesting thing comes in film boiling. So, these open circles are uncoated heater, okay, and we did 2 repeats, one for circle, one for triangle, and you see there is a very good repeatability in the data. The 10 micron carbon nanotubes, no change, okay, except that the Leidenfrost point probably happens a little at a smaller delta t. Okay. The interesting thing is the moment I go to 25 microns, and this is for 3 different subcoolings: saturated boiling, 5 degree subcooling, 10 degree subcooling. And what do I notice? There is almost a 3 times jump in the heat flux, 300% increase in the heat flux for 25 micron coated carbon nanotubes versus uncoated carbon nanotubes. And not only that, this is a very effective way to prevent or minimize the risk of an accident in a nuclear power plant, if we can make these carbon nanotube coatings. And since these are basically graphitic structures, they tend to be very radiation tolerant. Okay. Normally, if you put a material on top of a nuclear fuel bundle, because of the neutron bombardment, they tend to degrade over time. But carbon based materials are known to be, graphite type of materials are known to be very radiation tolerant essentially. So, this is actually a very good candidate for coating on fuel bundles and reducing the risk of failure. Okay. So, now so that is basically what you see from the carbon nanotube coatings. Then the thought was, can we make so based on this data that we looked at, we tried to figure out what are the mechanisms that are causing the boiling. Okay. So, we started the experiment thinking, oh, it is a high thermal conductivity, therefore bigger cold spots. Okay. But then the realization came, well, these are sticking out like hair, isn't it? So, I am effectively making a fin on a surface, right. Now, the question is, and we know this fin is causing disruption of the vapor layer. it might be causing a disruption of the micro layer, we do not know. Remember we talked about micro layer, where under the bubble you get this wedge shaped liquid that is trapped, and there is a controversy. Some people say it is 1 micron thick, some people say it is 100 nanometer thick, and it is only about 100 microns long, right. So, does the carbon nanotube disrupt the micro layer? We do not know. The other thing is, it probably enhances the liquid solid contact by forming that bridge. Okay. So, we started thinking about cold spots, but by the time we finished the experiments, we realized there is a nano fin formation. There could be some effect due to that, we do not know. There is a effect because of the disruption of the vapor film in film boiling, we know for sure, we see it in the pictures, but there are other things that could happen also. So, how do we determine that? So, we decided let us make a, so the big picture is which is more dominant, is it the conductivity effect or is it a shape effect, the nano fin, okay, which is more dominant. So, to answer that question we made nano fins. So, we took a silicon wafer and we etched these tiny fins by using a lithography or a imprinting technique. Okay, I will not have time to get into the manufacturing process, but it is a very interesting manufacturing process. Okay. And we made fins of different diameters. Okay. We made 200, 300, I am sorry, different heights. So, these were about 100 nanometers in diameter, to 100 to 200 nanometers in diameter, and we made them in height going anywhere between 10 nanometer all the way to 600 nanometer, and the pitch was somewhere between 800 and 900 nanometers. Okay. So, there are these 3 different types of fins you can see we have formed. Now, the question is, and if you look at it in side view, this is how the fins look like. And then what we did, actually it is not very visible in this picture, but if you look at the image on the TV, you will see that there are these thin lines that are there on the surface. Those are the nano thermocouples. So, we made the fins and then we deposited a nano thermocouple on it. And so, if I take an image, this is the chromel layer, this is the alumel layer, this is the junction where I am measuring the temperature, and these dots that you see are the nano fins. Okay. So, we made this structure and we did the same pool boiling experiment once more. And our expectation was, because this is silicon, it has a lower thermal conductivity, so it should give us lower CHF. Okay. Now, we got more than what we bargained for, because there were a lot of interesting things we found started happening. Oops. So, what we found was, as we plot the heat flux as a function of wall superheat, this is without coating, without the nanofins. This is with the nanofins. The onset of nucleate boiling happens at around 4 degrees Celsius, as we expect, right. Do we really expect the onset of nucleate boiling to be at 4 degrees? What did we say? Smaller the cavity radius, higher the wall superheat. And so, if I have if I have a 10 micron cavity, as we discussed in the class, the wall superheat was 4 degrees. But now I have a cavity which is 1 micron. So, my wall superheat should be 40, but it is still 4. So, that tells you that on the nanoscale, that value of sigma is probably smaller. So, when you form a nano bubble, that value of sigma is probably 10 times smaller than when you have a big bubble. Okay, this is the direct evidence of that, because otherwise if it were not so, right, number one, can we use 2 sigma by r, that is a big question, and if you can use 2 sigma by r, if it is still valid, that means sigma has to be smaller, and because there is a chemical concentration gradient on the surface of the bubble, right. We discussed that when we discuss the nanobubble part. Now, the other interesting part is with respect to the CHF. So, we had 100 nanometer, 250 nanometer and 300 nanometer pillars. And what do we see about CHF? It does not matter. All three pillars are giving us the same CHF, that is number one. Number two, it is 120% higher, carbon 60%. Okay. So, of course, it is not the thermal conductivity of the fin, it has to be the interface, is not it? We did not know until we did the molecular simulation, we did not know this part. But the more interesting part is if all the CHF values are the same, as long as your pillar size is more than 100 nanometers, that implies that your micro layer has to be 100 nanometers. Okay, because when I have a fin that is sticking out, okay, so what do I mean by that? Let us draw it out. So, let us say I have formed a bubble, and this is my micro layer, right. The big question is, what is the length of this micro layer? You know, the general consensus based on interferometry techniques is this is about 100 microns, but the big question is what is the thickness of this micro layer? And so, some people are saying this is 1 micron and some people are saying this is 100 nanometer. So, what our results are showing is, let me take out the colored pens. So, what our results are showing is if I have a fin, I have one fin which is 100 nanometers high. I am sorry, let us say this is 300 nanometers high. I have one fin which is 250 nanometers high, and then I have one fin which is 100 nanometers high, and I have one fin which is 10 nanometers high. Well, the 10 nanometer guy is not giving me much of an enhancement. Okay. So, that means, well, the part that is sticking in the vapor is not really conducting any heat, because vapor is almost an insulator. So, where is the heat getting conducted? It is only getting conducted here and here, is not it? It is getting conducted here and here, it is getting conducted here and here. So, as long as my pin, that fin height is more than 100 nanometers, rest of the height does not matter. So, that tells you that the micro layer thickness has to be of the order of 100 nanometers. This is a direct proof, okay, because optically I cannot measure it, it is below the wavelength of light. So, I cannot use interferometric techniques to go and measure the thickness. So, this is one way to prove that micro layer is indeed 100 nanometers thickness, because if it was more than 100 nanometers, then each of these fins would have given me different CHF. The fact that all of them are giving me the same CHF means only the first 100 nanometers of each of these fins is participating in the heat transfer, rest of it is insulated, right. Now, the bigger question is, why should I get twice the CHF? Okay. So, before we resort to the molecular simulations discussion, let us look at this concept of what is known as a interfacial resistance. Okay. So, let us look at all the resistances that are there in this network. So, I have a nano fin, sorry. So, I have a nano fin. Okay. If it is a carbon nanotube on a silicon wafer, well, there is a resistance in the wafer itself, because my heat is coming below the heater substrate, right. So, there is a resistance in the wafer, there is a resistance at the junction between the carbon nanotube and the substrate, there is a resistance within the fin itself which is R3, and then there is a resistance between the fin and the liquid, which is known as the Kapitza resistance. Okay. Now, let us look at how much these values are. Okay. The value of R3, I have said very low, but we can estimate this based on the diameter and thermal conductivity and so on. But if I look at the value of this Kapitza resistance, for silicon it is 10 to the power minus 11, for carbon it is 10 to the power minus 8. Okay. Now, the question is, why is the interface resistance so high for carbon? The reason is, carbon is a very good thermal conductor. Okay. What does that mean? It means the molecules, the carbon atoms in a carbon crystal lattice, they are vibrating at 6 terahertz. Okay. And heat is nothing but the flow of vibration. So, higher the vibration frequency, the faster the vibration travels in that material. Okay. Versus in silicon, that natural vibration frequency, okay, is of the order of 1 terahertz, 1 to 2 terahertz, 6 terahertz, 2 terahertz. Okay. What is the vibration frequency of the fluid molecules, the liquid and the gas? It is 0.5 terahertz. Okay. So, the vibration impedance, the impedance mismatch between silicon and the fluid is 2 terahertz, or let us say about 1.5 terahertz, versus the impedance mismatch between carbon nanotube and the fluid is 5.5 terahertz. Okay. So, the heat travels really fast in carbon, and carbon is doing this, right, and the liquid is doing this. So, there is a huge vibration mismatch and the heat is trapped in the carbon, it cannot jump into the fluid. Versus silicon, it is vibrating at a lower frequency and the fluid is doing this, but the mismatch is less, right. So, therefore, even though the heat travels at a slower speed in silicon, it is jumping much more efficiently into the liquid molecule. So, what does that tell me? I can come up with a graphene or a super graphene, and I can come up with these high thermal conductivity materials, but they will get killed by that interface resistance. Okay. So, the nanoparticle I want is the one that has that vibration more in tune with the fluid vibration when I am looking at liquid to solid heat transfer. Okay. That impedance mismatch becomes a big issue. So, now let us look at the real numbers. Okay. So, in essence, what we are focusing on is this resistance at the interface between the solid and the liquid, or what is known as Kapitza resistance. So, we write it as RK. Kapitza in I think 1907, 1908 was doing heat transfer experiments between a gold surface and liquid helium, and he noticed that there was a temperature drop that was happening going from the hot surface to the liquid helium. Now, when we teach you heat transfer, what do we tell you? The first layer of liquid that is in contact with the flat plate has the same temperature as a flat plate, but in reality that is not true. On a macro scale, when you look at it at a much lower magnification from above, yes, they seem to be the same temperature. But once I go to the scale where your the dimensions of the solid surface is the same as the intermolecular spacing in your liquid, at that scale there is a temperature jump that happens going from the solid surface to the liquid surface. Does that make sense? Okay. And so, that is the so Kapitza was not able to explain it, but he reported it that I am seeing this, and so that is why it is called Kapitza resistance. So, one good way to understand is it is not contact resistance. Okay. Contact resistance is something different. Okay. So, consider there is a carbon nanotube which has a crystal structure where there are, let us say 12 of these carbon nanotubes around one cylinder. Okay. Now, I go to another cylinder where there are 10 of these carbon nanotubes. So, I am going from a higher diameter tube to a lower diameter tube. It is the same material. Okay. But because this has a higher diameter, its radial frequency, breathing frequency is different, and this one has a different radial frequency, natural frequency, because the diameter is smaller. We know this from solid mechanics, right, from your vibrations and damping classes, isn't it? The diameter of your cylinder determines the natural frequency of the cylinder, isn't it? So, as a result what happens is the frequency, the vibration that travels along this tube, once it encounters this junction, a part of it gets reflected back, a part of it travels into the tube with a smaller diameter, and a part of that vibration gets scattered. Okay. So, there is a loss of temperature, going from this part to this part. So, this is my higher temperature tube, this is my lower temperature tube, and there is a jump. And so, there is a equivalent resistance which is voltage divided by current. Heat is the current, temperature is the voltage that is driving the current, and so this resistance is your interfacial resistance or Kapitza resistance. Okay. So, if I look at the Kapitza resistance, if I do the math, this is in direct numbers in meter square Kelvin per watt, but let us normalize these numbers. Okay. So, it is easier to understand. So, I have normalized it. So, in carbon nanotube the Fein resistance is 500 ohms, the interface resistance is 1000 ohms, the total resistance 1500 ohms. Okay. When I come to silicon, the resistance is about 700 ohms in the Fein, interface resistance ohm, total half. So, if resistance is half, potential drop is the same, current is twice, and that is what we see in the CHF. Silicon gives us exactly double the CHF of carbon. Okay. So, we have proved that it is not the resistance in the Fein, it is the interface resistance that counts, right. So, then we came up with a theory, we made a hypothesis which we called as a Nano Fin effect. So, if this hypothesis is true, what does it imply? So, instead of carbon nanotube, if I have a glass nanotube, silica nanotube, then this should be the resistance, total resistance, and it should be somewhere between carbon nanotube and silicon. And if I have a metal nanotube like nickel, then it has even the lowest resistance of all these guys. So, which means this one should give me the highest CHF, and a silica nanotube should give us a CHF that is in between carbon and silicon, okay, if this hypothesis is true. So, we pitched this as a proposal to NSF, we got funding, and sure enough we did the experiments, and so we are plotting the CHF as a function of this predicted total resistance. Okay. And sure enough carbon nanotube gives us the lowest CHF, next highest is silica, next highest is silicon, next highest is nickel, exactly what we predicted. Okay. So, it again proves that the interfacial resistance is what counts, that is what dominates the game. Okay. And if Nano Fin effect is not true, then CNT should give me the highest CHF, because it has the highest thermal conductivity, right, and silica should give us the lowest CHF, because of all these guys that guy has the lowest thermal conductivity, but we do not see that. Okay. So, that was a big sense of relief for us to figure out that we have proved something that was initially very counterintuitive. All right. Then in parallel we were also doing the nanofluids experiment. So, what is a nanofluid? Well, you take any base solvent, and if I can put nanoparticles in them, and if I can form a colloidal solution, which means the nanoparticles are stable over time. A good example of a colloidal solution is milk. You put milk in your refrigerator, the proteins do not settle out over time, the proteins are nanoparticles, right. So, for your nanofluid experiment to be valid, the first thing you have to prove is the nanofluid sample that you are working with is stable, it is a stable colloidal solution. If it is not a stable colloidal solution, then you will get all sorts of weird answers, okay, and unrepeatable experiments. Okay. So, repeatability is the first key parameter to make sure that your experiment has been done in a valid way. Okay. So, a nanofluid should compose of nanoparticles that form a stable colloidal solution. Unless it forms a stable colloidal solution, you cannot call it a nanofluid. Just putting nanoparticles in a solution does not mean it is a nanofluid. Okay. Now, why do people care about nanofluids? Well, people have shown that you can get viscosity enhancements, pretty high enhancements in thermal conductivity at mass loadings as low as 1%. So, these are all the the prior work in the literature showing percentage enhancements in the thermal conductivity. Okay. And then the realization in the community was, when you put nanoparticles in a fluid, viscosity goes up, it goes up as high as 400% in some cases. Your viscosity goes up by a factor of 4. So, it is justified to use a nanofluid, because I might get 10% higher heat transfer, but my pump has gone up by a factor of 10. Okay, it does not make sense. My pure fluid for that same pressure drop or for that same pump power will probably give me better cooling, is not it? So, nanofluids are not a universal solution. It depends on the type of nanofluid you are using, and depending on the synthesis protocol you choose, that same nanofluid can have different properties depending on how you are mixing it with the nanoparticles. So, the synthesis protocol is again a very important parameter that people do not pay attention. Okay. But our research group was the first to show that the heat capacity also goes up. Okay. And then the misconception in the literature was that the heat capacity should go down, and same thing with the boiling experiments also. All those film boiling data that I showed you, our group has been the first one and the only one that has done boiling on carbon nanotubes and silicon nanotubes, going from nucleate boiling all the way to film boiling, and then also for big heaters. Our heater size was 5 centimeters by 3 centimeters, and then 90% of the papers that you see in the literature these days are on 1 centimeter by 1 centimeter heaters with nano coatings on them. And then, as we discussed with respect to Taylor instability analysis, that is creating its own convoluted experimental data, because now you cannot really compare a plane surface with a nano coating surface, right. We had that discussion on Wednesday, is not it? Okay. So, if you look at the literature, there are all sorts of these experiments being done without proper thinking going into doing the experiments, into what exactly am I testing, right. Your objective should be clear before you start designing your experiment. So, with respect to the nanofluids heat capacity also, this Nelson, Ian Nelson and I, we went to Air Force Research Lab. That was the first year we showed there was a 50% jump in the heat capacity using graphite nanoparticles, and subsequent to that we proved with molten salts. And then now we are seeing papers all across the world where people are actually replicating our experiment, and they are coming up with their own theories to explain why it is so. Okay. But for 3 years we did not sleep at night, because we thought we were wrong, because we were the only ones saying it goes up and nobody else was saying it. Okay. So, why does it form? So just to recap, you have Lennard-Jones potential. So, when two molecules approach each other, they have a equilibrium spacing in between them given by this, and what that means is it creates a surface adsorption on a solid surface. So, in other words, when I have a solid surface and liquid or vapor on top of it, well, a part of the fluid molecules, they get adsorbed on the surface and they form a higher density layer, and so surface adsorption causes. So, even though in the bulk the fluids are spaced far apart, near the surface they start layering up and forming an ordered structure, and that ordered structure is very similar to that of ice or the solid phase of that liquid solvent. And so, in other words, this adsorption causes a mechanism for trapping energy or storing heat. Okay. Now, how do I measure it, or how do I simulate it? So, a good way to do it is using molecular simulations. How does it work? Well, typically you take a carbon nanotube or any nanotube that you want to study a nanoparticle, you put it inside a computational volume, and then you fill it up with molecules that you want to study, and then you heat up the nanoparticle to a particular temperature by increasing its vibration energy. Okay. You let it equilibrate, and then you look at the rate of temperature decay with respect to time, which is this plot over here. This is the log of dt, rate of change of temperature with respect to time, and then you measure it, you plot it as a function of time. Now, if you remember, when we went to Newton's law of cooling, remember I said the time constant is proportional to the resistance times the capacitance divided by the area. Remember we had that discussion. So, this rate of change, the slope of this graph is your tau. The capacitance of the nanotube, I can look it up from a chart. The area of the nanotube, I know that is based on my size of my computational cell, and so I can back out the value of the Kapitza resistance. That is how the calculation was done. Okay. So, now that you know on a very broad overview how molecular simulations work. What is the implication of this simulation? Okay. So, this is the implication of this simulation. So, we did so this is taken from Navdeep's thesis, actually we subsequently published this as well. So, what happened was, here is your carbon nanotube that is vibrating because it is hot, and right around that the molecules, the solvent molecules have started layering up, and you can see there is a gap here. Why is that gap? Can somebody tell me? What is that? Nope. Right. So, the equilibrium spacing in Lennard-Jones potential, remember that, right? That is the equilibrium spacing, that is of the order of about 5 angstrom, that is the equilibrium. 0 to 5 angstrom there is nothing. Okay. And right after that I see the molecule has adsorbed on the surface and has formed a higher density layer. So, if I plot the density as a function of distance, this is my void space because of the equilibrium spacing of about 5 angstrom, and then I see a peak in density, this layer, very high density layer. The second peak is this layer, and you can see the density peaks are going down exponentially, and this is the bulk value. How much is it? 1.8. What is the peak value? Almost 1.6, double. So, the density because of surface absorption has almost doubled. Interesting, isn't it? Okay. Now, you can say, oh, it is a computer model. How do I know your model is correct? Isn't it? You make mistakes in your model all the time. So, the only way to believe a model is if you validate it against the experimental data. Okay. So, let us look at some experimental data. This is not my data. This is a paper that came out in Science. This is a sapphire crystal, this is liquid aluminum. What do you see? A high density layer of liquid aluminum has formed right next to the sapphire crystal, and they have plotted the density. They measured it from the image. You can see the density has peaked. Do you see that? And then the density falls off as you move away from the surface. Not only that, look closely. See, this is the first layer of the atoms of the sapphire crystal, the first layer of the atoms of aluminum. They have layered up as if they are part of the crystal. Okay. So, solid aluminum, let us say, has a BCC crystal structure, okay, body centered cubic. Let us say this one has a face centered cubic crystal structure, isn't it? What is the structure of the solid aluminum here? Is it BCC or FCC? So, in its natural state, aluminum is BCC. In that interface, it has formed a FCC solid. What is the property of FCC solid aluminum? I do not know. So, in other words, this semi solid layer that I have formed here has properties on the nanoscale that are vastly different than you would get in the bulk phase. Same thing about the surface tension. The surface tension that you get in the bulk phase might have a different structure than the surface tension that you get on the nanoscale, exactly on those same lines, okay, because the container now has started affecting the property of this layer. So, remember when we were talking about hydraulic fracturing, and I said depending on the container in which you put the liquid, the viscosity can change and the heat capacity can change. This is why, because now if I put a sapphire crystal on this side, which is about, let us say, 10 nanometers, now more than 50% of this trapped liquid aluminum here is going to be FCC liquid aluminum, not BCC liquid aluminum. FCC, BCC, I am saying it in loose terms, but you understand the concept I am getting at, right. So, the crystal structure of your container now starts affecting the crystal structure of your liquid inside it, and so therefore, the properties of the liquid start changing depending on the container you are putting it in. So, when you put it in a big container, that layer is tiny, but the moment I start shrinking the size of the container, Now, the walls of the container start affecting the properties of the liquid. So, that is one of the very interesting thing about multi-phase flows on the nanoscale, that properties, things like viscosity, heat capacity become a function of the contact angle of that container, which is very weird, right. We do not expect the contact angle of my glass to affect the properties of the ice that forms inside the glass, but it does when you make them very tiny structures. That is the interesting part of this whole topic. Okay. So, now that I have shown to you and proved to you that it does exist in nature, people have taken pictures, and this is not the only example. There are probably 20 or 30 of these studies that have shown it, and this is not today, this has been done 20 years ago. Okay. It is as heat transfer engineers, as heat transfer scientists, we are realizing the implications that condensed matter physics community already showed exists 25 years ago. Condensed matter physics community predicted this, showed this 25 years ago, but we as heat transfer people are now realizing the implications for our own work, what they discovered 25 years ago. Okay. So, now the interesting thing is that same chemical, if it has different chemical structure, will layer up in a different way around the nanoparticle. So, it is not only the chemical formula, but the chemical structure now becomes an important parameter. And so, Navdeep in his thesis showed that each of these different molecules, they are the same chemical formula, it is the same C16H34. Okay, but depending on whether it is a straight chain or a branch chain, or depending on how many number of branches you have, the Kapitza resistance was changing. Okay, this is something that we do not consider in a heat transfer textbook. We just say it is a oil, and here is the chemical formula, and we do not care about the chemical structure. But when you are dealing with multi-phase flows, especially on the micro and nano scale, you got to take into account the chemistry and the chemical properties of the coolant as well. Okay, that becomes a big issue. Okay. Now, so we did some nanofluids experiments. So, what we did was we used some compact heat exchangers. So, here is a compact heat exchanger. On one side I have a hot oil flowing, on the other side I have a cooling water cooling it down, and then we have a heater that was heating up the oil and it was getting cooled in the heat exchanger. Okay. And then we repeated the same experiment, except we put some nanoparticles in the oil. Okay. So, we expect the heat capacity to go up, thermal conductivity to go up, right, and therefore, the performance of the compact heat exchanger to change, is not it. So, we did the experiment. This is a picture of the experimental apparatus at Air Force Research Lab, and Dr. Rengaswamy Punnappan was my host, who kind of forced me into doing it. I did not want to do it, frankly, but now I am very thankful that he forced me into this topic. So, so here is the data. This is my heat flux plotted against a function of flow rate. The red circles that you see are pure oil. Okay. Then I put about 0.3% my mass of graphite nanoparticles, that is the blue dots, and then I put 0.6% my mass of graphite particles, that is the green dots. Okay. And I see about a 10% increase in the heat flux and the convective heat transfer coefficient, nothing new. 100 people before us had done the same experiment, they had gotten very similar data. Okay. But we went back and looked on the surface of the heater. This is the surface of the heater before the experiment, and these are the type of nanoparticles we were using. Okay. After the experiment, I went back and looked at the surface. It is actually not very clear on the screen here, you should look on the TV, and if you look on the TV, you can see a lot of precipitated gunk, just like Professor Das showed yesterday. Okay. And they were sticking out as if they were forming fin like structures. So, then again the question comes in, just like we saw in boiling, how much are the fins contributing to the heat transfer, and how much of it is because of the thermal conductivity or the heat capacity increase of the fluid. Okay. So, to answer that question, so here you can see very clearly, when we did the experiment with carbon nanotubes, they had precipitated as a bundle. You can see a bundle of nanotubes. These individual nanotubes have formed a braid, formed a big fin, and precipitated on the surface and sticking out from the surface. Okay. So, to answer that question, we got a funding from Qatar Foundation in Doha, which is their national science foundation, or you can say that is their Department of Science and Technology sort of. So, we made a micro channel, and we put these nano thermocouples in the micro channel to measure the temperature along the micro channel. Okay. and then we did the experiment with water, we heated it from below, and then we repeated the experiment by putting nanoparticles in the water, silica and titania, which dissolve right away into water, give you a very stable colloidal solution, and that would be the end of it. But then I asked my PhD student, can you repeat the water experiment once more after you are done with the nanofluid experiment? Okay, that's something that people don't know or don't do. They do water, they do nanofluid, end. Okay, but I said no, repeat the water. Okay, and then the results we got was very counterintuitive. So it's a very complicated story. We don't have time to get into all the nuances, but I'll give you the highlights. Okay, so look at this graph over here. The blue dots that you see are pure water, heat flux, flow rate. As I keep increasing the flow rate, my heat flux goes up. That's expected. I put in nanoparticles at 1% concentration, those are the red squares, and it goes up. Nothing new, nothing surprising. We got what we expected, right? Now we repeat the water experiment once again, and we expect, those are the green dots, and we would expect those green dots to lie up with the blue. They don't, they stay at the red, but it's pure water, but it's giving me nanofluid heat transfer. So what's going on? So you go back and look on the surface. Oops, sorry. Okay, my slides are a little disordered. I apologize. I thought I had corrected it, but maybe I did not save it right. So let me fish out that picture. Right here. So when I look at the substrate, I can see nanoparticles have precipitated, and they have formed nanofins, and they have not disappeared once I started pushing water. They are stuck to the walls of the heater. What does that mean? That means the thermal properties of the nanofluid are secondary. It's the nanofins that are dominating the game, because once the nanofins form, it doesn't matter whether you are flowing pure water or nanofluid, you are getting the same heat transfer. So that means the nanofin formation is the more dominant mechanism here. A simple experiment gives you so much insights, right? And so maybe the higher thermal conductivity and the heat capacity of the nanofins is a consideration, but they are a secondary role. The primary heat transfer, the primary component is the precipitated particles. That's what is dominating the game. Okay? So what does that mean? So to further prove this concept, what we did was we started making nanofins which were of the same size as the precipitated nanoparticles. Okay? So we formed these nanofins by etching, just like we did for boiling. These were about 750 nanometers high, about 100 nanometers in diameter, and we made them in a perfect square row array, and in parallel we also did one more experiment where we took a flat microchannel. Okay, we put a nano thermocouple in there, and we are measuring the temperature at this junction. If I look at it in the side view, that's my nano thermocouple, and I measured it using a confocal microscope. Now the advantage of the confocal microscope is I can focus in 1 micron intervals, okay, and I can measure exactly where I focused it, okay, and what I am measuring is the intensity of emission. So in one case I pushed a dye which is not a nanoparticle, and I looked at the temperature gradient by measuring the amount of emission coming out of the dye. because the amount of emission from a dye is proportional to the temperature. In the other case, I put these nanoparticles called quantum dots, and the light coming out of a quantum dot is again a function of temperature. Okay, you excite it with a laser and then you measure the emission coming out. So, once you excite it, the emission that comes out is proportional to the temperature. So, with 1 micron resolution, I could measure the emission intensity as a function of height. Okay, and based on that, I could plot the temperature gradient near the wall. Okay, so those are the data: quantum dot, dye, temperature gradient values. So, your heat flux is equal to minus k del T del y. Okay, so I am measuring the del T del y, and so what do I notice? For the dye, the del T del y is about 2 to 4 times smaller than that of the quantum dot. Okay, that is a very fundamental observation, because the way people usually measure thermal conductivity is they take a hot wire, they put it in the cold fluid, they measure the rate of heat loss from the hot wire, then they take that same hot wire, they put it into a nanofluid and they measure the rate of heat loss from the hot wire into the nanofluid, and they take the ratio of the two heat transfers and say that is my ratio of the K. They assume the del T del y is the same, but this one is showing that del T del y also changes when you have a nanofluid. Okay. Why should it change? Well, because the nanoparticles have precipitated, so your effective surface area of the heater has gone up. Okay. So, you are actually pumping more heat than a plane surface would, and that manifests itself as a higher del T del y. Okay. But that is not captured in your hot wire experiments, because in a hot wire you are going to get precipitates of this nanoparticle. Now, the effective area of your hot wire has changed, and so you are saying that ratio of the two Qs is the ratio of the two Ks. Well, but the ratio of the two areas are different and you have not accounted for it. Does that make sense? This is one of the big fundamental flaws of nanofluids literature, is they do not take into account the precipitation issue. Okay. So, then to trace it further, we made these nano fins, we put it inside the microchannel with these nano thermocouples in them. So, this is my K type once again, chromel, alumel. If I magnify it, this is how the junction looks like, and you can see these dots, those dots are the nano fins. Okay. And we do a heat flux versus flow rate graph. We plot the Nusselt number as a function of Peclet number. This is pure water without any nano fins. This is pure water with fins, and you can see a jump which is of the order of 20 to 80%, and it mimics our nanofluids experiments. So, this definitively shows that these precipitated nanoparticles are the ones that are giving you the enhancement, okay, which actually has a very fundamental implication. So, let us say I have a big heat exchanger in oil and gas plant or a chemical plant, this is the size of this room, for example. So, one way to make this heat exchanger more efficient is to put nano fins on the surface of the heat exchanger, right, which means I have to take it all apart, print nano fins, again push it back. The other way is you take the heat exchanger, flow nanoparticles for 2 hours, let the nano fins form, go back to flowing your pure water. You are going to get a better performance without the pump penalty of a nanofluid, isn't it? So, repeating that water experiment twice gives you a commercial implication, that you can take an existing heat exchanger, use your nanofluid to get a nano coating, and go back to flowing your pure fluid. You get higher heat transfer with the same pump penalty. Okay, so, that is one implication of this work. So, basically if you look at it, the duration for which you do the experiment also matters, because if you have isolated precipitation, it gives you a nano fin, you get a very high heat transfer, boiling heat transfer or single phase. But if you get too enthusiastic, you put too much nanoparticle concentration, or you do the experiment for too long a time, you get excessive precipitation, you get fouling or scaling, and your heat transfer actually goes down. Okay. So, you have to be very careful when you design these experiments, because the time for which you do the experiment becomes a big crucial factor. But if you can control it right, you can actually cause heat transfer enhancement, okay, with the the proper optimized design of your experiment. Okay. The second implication of this work is that your heat capacity goes up. Okay. So, this is for graphite, this is without graphite nanoparticles, this is with graphite nanoparticles, specific heat as a function of temperature. Same thing with carbon nanotube, without nanotubes, with nanotubes, there is almost a 50% jump in the heat capacity. And so, we decided to use it for solar thermal application. So, what happens in solar thermal? You have a bunch of mirrors that focus the light onto the top of a tower, and you have a container there that contains salt, and when you heat it up to about 500 degrees Celsius, it melts. Okay, about 300 degrees Celsius it melts, and then you take that molten salt and you generate steam out of it. So, you concentrate the solar power onto this tank, this tower, and it has molten salt. The molten salt comes out at about 600 degrees Celsius, gets stored in a hot tank. Okay, then you take a part of that salt, hot salt out, pass it through a heat exchanger, generate your steam, generate your electricity, and then the cold salt at about 480 degrees or 300 degrees or so gets into this tank and gets pumped up here. Okay. So, even if you add nanoparticles and the viscosity goes up, you are not running the pump 24 hours a day. Okay. So, your pump energy is much lower because you are not using it for a cooling application, you are using it as a thermal battery application. You are using it to store your thermal energy, just like you store electrical energy in a battery, you are storing thermal energy in a thermal battery. Okay. So, we pitched to DOE, let us put nanoparticles. In the interest of time, I will skip the radiation discussion here. And so, what we found was, when this is your pure molten salt, has a heat capacity of 1.6. When we were putting silica nanoparticles in there, it jumped to 2 joules per gram Kelvin at 1% concentration. Why is that? Well, the moment you put nanoparticles, it forms an ice layer around it, and the ice layer has a different heat capacity. It is of the order of 6 joules per gram Kelvin is what we are estimating of that ice layer. So, this guy is 1.6, this guy is 1, the nanoparticles are 1, but the ice that is forming, the solid phase of the molten salt that is forming around that nanoparticle is expected to have a heat capacity of the order of 6 joules per gram Kelvin. Okay. So, if the nanoparticle is below 10 nanometers in diameter, for every 1% nanoparticle I put in, I get 5% mass fraction of the ice layer. Okay. And that 5% mass fraction has a heat capacity of 6. So, if you do the math, if you use this equation, x times the Cp of nanoparticle plus 1 minus x times the Cp of the particle of the fluid, this is wrong, because I have not taken into account that compressed layer. So, if I take this as 1%, this as 1, this as 5%, and this is 6, right, this is about 90.95 or 9.94 times 1.6. You add it up, you get 20% enhancement. Okay. So, we proved that this compressed phase forms a storage. So, that acts like a capacitor. Okay. So, if you do molecular dynamics simulation, you can estimate the thickness of that ice layer, and that goes into your capacitance calculation. Okay. Basically, now your capacitance has 2 parts, the capacitance of the solid, the capacitance of the compressed phase, and these two together form a parallel capacitor network, and if you sum it up, that gives you the total capacitor. Okay. And you see that there is an enhancement in the capacitance by as much as 50%. Okay. So, that is your storage. The last part comes in is what is the diode. Okay. That is the last part I wanted to discuss with you all. So, we have discussed the resistor, the capacitor resistance, we have discussed the capacitor, the ice layer. Now, the big thing is, what do I mean by a diode? Okay. What is an electrical diode? In an electrical diode, when you change the positive to negative and negative to positive, the current goes down by a factor of 10. Okay. When the diode is in the forward orientation, let us say you are getting 1 milliamps of current, the moment you switch the terminals, that current now goes down to microamps, isn't it? That is the principle of a diode, that if you change the polarity, the current goes down by a substantial margin, versus for a pure resistor, it does not matter. If you change the polarity, the current is still the same, the magnitude of the current is still the same, right. So, nanoparticles act like a thermal diode, which means if I have a hot nanoparticle, I will actually pump more heat into the liquid, versus if I have a cold nanoparticle, I will actually pump less heat from the liquid to the solid, even though the temperature drop is the same. So, in other words, if I have a liquid which is at 50 degrees Celsius, right, I put in a nanoparticle at 60 and I put in a nanoparticle at 40. So, the temperature drop is the same, but the hot nanoparticle will probably pump about 10% more heat. Okay. So, if the hot nanoparticle is pumping 1 watt of power, your cold nanoparticle is expected to pump only 0.9 watts. Okay. That is the implication of this model that I am going to show you next. Okay. So, now that I have formed this compressed layer, right, that means I have a higher density right next to the nanoparticle and lower density of the fluid away from the nanoparticle, isn't it? So, now I have created a density gradient or a concentration gradient. Does that make sense? Okay. So, when I have on the hot nanoparticle, the temperature gradient and the concentration gradient are in the same direction. Agreed? Okay. When I have a cold nanoparticle, my temperature gradient is in one direction and my concentration gradient is in the other direction. So, they are opposing each other. Okay. Now, how many of you have heard about this term called Dufour effect? Any of you heard this term called Dufour effect? How about Soret effect, SORET? Any of you heard Soret effect? Come again? Thermal diffusion. Because there is a temperature gradient, it causes a mass of material to move from hot to cold, because there is a convection that has been set up. So, because there is a convection current, material is moving from the hot place to the cold place, right. So, similarly, just like you have a Soret effect, you also have something known as a Dufour effect. So, here because there is a mass concentration gradient, it can take a cold fluid to a hot fluid, because the cold fluid is at a higher concentration. Okay. So, I wanted to show you other stuff, but unfortunately we ran out of time. We also came up with a concept where you do not have to add nanoparticles, you can add unstable chemicals. When you heat them, they degrade. Okay. A good example is soap. When you microwave soap, it generates carbon nanoparticles. So, be careful what you put in your microwave. Okay. If you do not clean up your bowl and it has soap in it and you put water to heat up the water, chances are that soap that is dissolved in the water is making carbon nanoparticles for you. So, you are probably having carbon onions in your soup, if your soap has not been taken away. Okay. So, here is the example. So, we put this additive which is a surfactant SDS or SDBS, we put it in the molten salt and we heated it up, the heat capacity went up and we were thinking what happened, and then we look at it and we see we are forming carbon onions. Okay. And so, the carbon onions are increasing the heat capacity. What does that mean? Well, nanoparticles are $1,000 a kilogram, your salt is 40 cents a kilogram. If I put $1,000 a kilogram nanoparticle even at 1% concentration, my cost of my material has gone from 40 cents to $1.40. So, I better have 4 to 5 times the conductivity enhancement or heat capacity enhancement to justify that additional cost, isn't it? Versus this additive approach, these salts and soaps that generate the carbon onions, they are 20 cents a kilogram. So, even if I put them at 5% concentration, my cost has gone from 40 cents to 42 cents, but my heat capacity has doubled. So, my dollars per kilowatt hour or rupees per kilowatt hour has gone down by a factor of 30%. Okay. So, instead of explicitly putting nanoparticles, putting this additive that generates nanoparticles on demand means every time you heat it, it is generating nanoparticles for you. Okay. And that is a much cheaper way to get your job done. Okay. So, that was one approach, and what we found was, so this is the cost analysis. If I put nanoparticles, my cost has, this is 40 cents a kilogram, nanoparticles are $200 a kilogram, my dollars per kilowatt hour has gone up by a factor of 2. But if I put this additive, this is pure salt, and with the with the additive approach, the cost of storage has gone down by a factor of about 20 to 30%. Okay. My storage cost in terms of the amount of electricity I am producing the cost of electricity has gone down by anywhere between 20 to 50%, because of the storage. Okay. So, so in summary, we are out of time, so let me summarize. So we have actually built a flow loop where we can test this at 600 degrees Celsius, these molten salts with and without nanoparticles. So this is a work in progress now in our lab. Okay, and this pump that you see over here is a $30,000 pump. This is the same size pump that is used in a solar thermal power plant. So we are doing a 2-scale testing actually for a power plant. We are also doing some 3D printed heat exchangers. I didn't get to talk about it. And the boiling chaos, unfortunately, I ran out of time. So using these nano fins, using these nano thermocouples with the carbon nanotube coatings, you can see the temperature fluctuation when we are in film boiling versus critical heat flux versus in nucleate boiling. The fluctuations are different. Okay, and if we do a phase plot of these fluctuations, we can see that there is 2 poles. There is 1 pole here, there is 1 pole here, and the system is oscillating between these 2 poles. That's characteristic of boiling chaos essentially. I'm sorry I didn't get time to explain this in detail, and you have to use information theory principles to generate these plots actually. So there is a lot of complexity in this topic. So maybe we can do a Gyan course just focus on boiling chaos and boiling fractals essentially. So basically in conclusion, this 1-step procedure for making nanoparticles, which is putting additives that generate nanoparticles, is very critical. It has good scope for industrial application because it enhances thermal properties, there is good stability, it reduces corrosion, and you can scale up in a very cost effective way. You can make tons of these. In a typical solar thermal power plant, the storage is a 30,000 ton tank of molten salt. It's not possible to add 200 kilograms of nanoparticle and start it up in a 30,000 ton molten salt facility, right? It's much easier to pour buckets of soap and let that soap generate the nanoparticles for you, because soap will diffuse on its own. You don't need to start up soap, isn't it? Okay, so this is actually much more easy to scale up to tons and tons of synthesis. We came up with a simple analytical model, that x times Cp, y times Cp of compressed phase, that shows that the contribution of this compressed layer to heat storage, and we also looked at the rheological properties. I didn't get time to discuss that. And so in summary, the interfacial resistance or Kapitza resistance dominates the conduction thermal resistance of the whole critical heat flux. The thermal capacitance of the compressed layer serves as your heat storage, and then the heat transfer bias, because of concentration gradients, the diode effect also modulates your heat transfer. But the fundamental insight we get from all of these is, what is the more important parameter? Is it the nanoparticle, or is it the compressed layer properties? So when you are designing an experiment, you look at the literature, people are running after the nanoparticle, but all the nanoparticle does is gives you a lot of surface area for that compressed layer to form, but nanoparticle is not driving the enhancement. What is driving the enhancement is the solid phase properties of the liquid. So you should be paying more attention to your choice of solvent, particularly the solid phase properties of the solvent. That is what is causing the enhancement. Okay? So the fundamental insight we get is, all these enhancements that we see is affected more by the fluid composition than the composition of your nanoparticles. Okay? Nanoparticles matter because not all nanoparticles are going to give you stable colloidal suspension. So your choice of nanoparticle is to make sure that you get a stable colloidal suspension. That's it. Your enhancement will come from the choice of your fluid and the fluid composition. That was the fundamental insight, which was very counterintuitive to what's out there in the literature that we gathered from this study. Okay? So again, I would like to acknowledge my students. They did all the hard work, and these are the funding agencies, my collaborators, particularly Dr. Sinha I mentioned, Shayan Sinha, where is it? Yeah, at the University of New Haven. He helped me set up the carbon nanotube furnace in a week, and of course my other collaborators from other projects, particularly Dr. Rengaswamy Ponnappan, where is his name? Yeah, that same at Air Force. He forced me into doing nanofluids. I did not want to do it, but it's a gift that still gives, giving essentially. And then these are my collaborators from the DARPA center. The molecular simulations work was developed from this particular funding. And then finally, that's my contact information. And thank you for being very patient with me all through the Gyan course. Afternoon session is with Dr. Bhattacharya, and then you have your quiz. So before we depart for lunch, any questions? Go ahead. Mm-hmm. Doesn't matter. It depends on your materials consideration. As long as your container walls can hold it, you can go as high as you can. You mean the diode effect? So yeah, I guess you could think that there would be more nonlinear effects, because what we did was here we considered a model which is low mass transfer model. When you get to mass transfer, there are two limits in mass transfer. Okay, there is a low mass transfer limit and there is a high mass transfer limit. Okay, the equations that you see over here are the low mass transfer limit equations. Okay, at certain, if you exceed a certain critical value of delta T, you go to the high mass transfer limit equations. Okay, and then it's a completely different ball game. Okay, so the difference between low mass transfer and high mass transfer, your perspiration from your skin is a low mass transfer limit. Okay, combustion of a soot molecule is a high mass transfer limit. Okay, so the type of equations you use for these two different cases is completely different. The models are completely different. So I would assume that if you exceed a certain temperature difference, then you have to do the same model with a high mass transfer limit models. But these conclusions that we drew were for low mass transfer limit. So if you go to high mass transfer limit models, the diodicity will be even higher. So what we are predicting 10% for nickel might go to as high as 30%. Okay, which means you will get 30% less heat transfer going one way compared to the other way. Does that answer your question? Okay, all right. Any other question? Exactly. So to begin with, the heat capacity of that layer is so much higher, right? That's one part. And then the second is, if your nanoparticle is smaller than a particular size, particularly below 10 nanometers, okay, then for every 1% by mass of nanoparticles you add, you are creating about 5% by mass of that ice layer. Okay, that's the second part. The third part, which I did not get to talk about, is the formation of tentacles. Okay, so if you go to the image, you can see that they have these ice layers have actually formed tentacles. Give it a second, it will come. See this image over here? I have formed the nanoparticles. You can see the dots. The white dots are the nanoparticles. You see this dot here? That's a 40 nanometer nanoparticle, right? And I have formed a ice layer around it. But is the ice layer isolated? It's not. It has joined up with the next nanoparticle. I have ice layer, nanoparticle ice layer, nanoparticle ice layer, they have formed a tentacle. So I have not accounted for that mass, right? I have only accounted for the mass of the compressed phase around the nanoparticle. But I have also formed a tentacle which is the compressed phase, and that is also adding to the heat capacity. So there are two questions that come in. Why did this tentacle form? Okay, that's one question. And what is the composition of this tentacle? Okay, what do I mean by that? There are so many nuances I skipped. You can see that, right? There is a much bigger story. I am just giving you the introduction to the chapter. You are reading a novel and you are reading the first paragraph of each chapter. there are 5 other paragraphs in that chapter that I did not get to discuss with you. Okay, so there is a much rich and complex phenomena in multiphase flow occurring in nanoscale that I didn't get to discuss with you all. Okay, so I'm going to give you one more chapter. There are more chapters to this. Okay, but let's look into the second chapter since you asked the question. So I have a nanoparticle, right? Okay. Let's say this is a solar salt, which means I have 60% sodium nitrate, 40% potassium nitrate. Let's say I have a silica nanoparticle. Guess what? If I do the Lennard-Jones potential between silica and sodium, and I do the Lennard-Jones potential between silica and a potassium atom, well, because sodium is a smaller molecule than potassium, silica tends to like it more. Does that make sense? Okay, which means I am going to get more sodium atoms or ions around the silica nanoparticle and less potassium ions around the silica nanoparticle, which means my bulk composition is 60-40, but around the nanoparticle I have probably formed a 70-30. So 60-40 is a eutectic. It melts at 480 degrees Celsius or 300 degrees Celsius. The 70-30 probably melts at 400. So I have formed this ice layer around the silica nanoparticle that has a higher melting point than the bulk. That's the first part. Okay, the ice layer has a different melting point, just like we showed for the hydraulic fracturing. The bubble point goes up, the melting point goes up as well. Okay, so that's the first implication. The second implication is, let's say I have one silica nanoparticle. I have one silica nanoparticle. Here the concentration is 60-40. Here the concentration is 70-30. What has this caused? A concentration gradient coming from both sides. So now this silica nanoparticle starts forming tentacles in the direction of the concentration gradient. So now I have formed a rainbow that's going from 70-30 to 60-40 to 70-30. If I were to plot this concentration in a sort of a rainbow sort of color fashion, so let's say it's more red here, less red here, and again more red here, depending on the concentration of sodium, I have formed this rainbow sort of tentacle, where the color of that tentacle changes as the concentration of the sodium is changing. So which means I have formed this tentacle where each part of the tentacle has a different melting point, and each part of that tentacle has a different specific heat capacity, because your heat capacity now is some nominal heat capacity corresponding to 60-40 plus some concentration, constant time concentration square, some constant time concentration cubed, and so on. As the concentration varies, the gradient of the concentration varies, the net heat capacity varies, and now you got to measure it, multiply it against the, if I chop it up into sections, for each section there is a different heat capacity, the next section has a different heat capacity. So I got to add up the heat capacities for each section and then get the total heat capacity of the mixture. So you see how complex the situation is, and the description I gave you was a very simplistic description in times the x times Cp1 minus x of the compressed phase, and that's only around the nanoparticle. Now if I account for that tentacle, it gets to be a more complex analytical model and a more complex interaction between the nanoparticle and the solvent. Okay, so that's where that additional enhancement is coming from. It's not just a thin layer around the nanoparticle. So in other words, if I look at this network, how does it look like? It looks like a bunch of these tentacles moving in different directions, and wherever there is a junction, there is a nanoparticle. That's how the picture looks like, isn't it? So it has formed a percolation network. So what does a percolation network means? If I put a current in this resistance network in any part of the structure, it gets distributed into the percolation network. So, the heat does not need to travel through the liquid, the heat just travels through the percolation network, because this is semi crystalline. So, this has a higher thermal conductivity, higher heat capacity, and this is what causes the viscosity to become non-Newtonian. So, the same fluid, the moment you put nanoparticles, becomes a non-Newtonian fluid. I did not get to discuss that, we ran out of time. Okay. So, this multiphase flows that you get on the nanoscale is a very rich novel, okay, that we are writing right now, and we are writing one chapter at a time, and each chapter gets more and more suspense and more interesting and complicated. The plot actually becomes thicker, actually go down the road. Okay. And I just gave you a simple introduction to a much richer physics that is happening underneath. Okay. So, it is a complicated love story, let us put it that way. So, all right. So, with that, let us stop here. Any other questions? Sorry, I did not mean to stop here. Any other questions? Or, and so should we start at 3 or what do you say, because it is already 1. Mm-hmm. Oh, about 800 nanometers, roughly 1 micron. Good question. Okay, that's another chapter of the novel we didn't get to discuss. All right. So, what is your typical size of your bubble? I am not talking about a nano bubble, I am talking about a heterogeneous nucleation. So, in heterogeneous nucleation, your typical bubble size for nucleation to occur is of the order of about 5 to 10 microns. Okay. A good way to understand that is, I did not get to talk about the boiling chaos part. So, if you look at the pictures in the boiling chaos, that is actually very illustrative. Yeah, and I did not get to talk about the spray boiling either. So, there was some interesting movies I wanted to show you, but probably some other time. So, when we were making these nanoparticle coatings, right, carbon nanotube coatings, what we found was this carbon nanotube coating was not very uniform. At places it was forming these cavities. Okay, so it is not very clear on this screen, but if you look on the TV screen, look at this bottom picture over here on the TV screen, you can see it has formed a cavity which is of the order of 20 to 70 microns in diameter. You see that? That means this cavity is going to nucleate a bubble which is of the order of about 20 microns, let us say. Okay. So, if I look at it in a sort of a schematic way, so let us say I have formed this 20 micron bubble. With the micro layer in there, right. And I have this bunch of nano fins that are sticking out, which are on a 1 micron interval. Whether they are carbon nanotubes or whether they are silicon nanotubes, it does not matter. And as Professor Dash was explaining yesterday, if I look at it in a sort of a magnified scale, I am pumping, I am having this evaporative resistance, the thermodynamic limit of evaporation at over here, isn't it, because it is a thin film. And the moment I have formed a microfin or a nanofin that is sticking here, I am forming that same dynamics here also, because I have a wedge of liquid trapped here, which is also of the order of 100 nanometers. So, I am causing a thin film evaporation here as well. Okay. So, these zones of thin film evaporation have increased, that is one part, and then the second part is only the first 100 nanometers is participating. After that it is not participating anyways, because the rest that is sticking in the vapor bubble, it is in an insulated region. So, it is not helping with the heat transfer anyways. So, that explains the 100, 200, 300 giving you the same CHF. Okay. But more fundamentally, if I look at it, this is how realistically it looks like, that your bubble is much bigger, the bubble that has nucleated from the cavity here is much bigger than the gap between the nanofins. And then the second part is, if I want to form a bubble in between these nanofins, okay, the amount of superheat that I will need to form that is thermodynamically very prohibitive, because your availability is not going to be that much. The availability that drives the formation of the vapor bubble, that availability is much lower compared to the availability of forming a bigger bubble from the cavity. It is a competing process, right. Okay, I can form the bubble in between the nanofins, or I can form the bubble in the cavity. Guess what? The change in availability for the bubble to form in the bigger cavity is bigger. So, this has a higher probability of happening than this. Okay. This probably forms, I do not know. Okay. We have not seen it, but it might be forming for all you know. And so, there is another theory in boiling which I did not get to discuss, which is known as the weakability theory. Okay. So, according to the weakability theory, I am looking for my green pen. These nanofins, they serve as a porous surface. Okay. So, what Dr. Bhattacharya is going to describe in the afternoon is microporous boiling, but these nanofins effectively have formed a nanoporous surface. Okay. Now, what is the fundamental limit for critical heat flux? The rate at which I can take vapor bubbles away from the surface, right. But the other limit is how fast can I replenish that liquid that has become vapor, how soon can I fill it up with liquid. Okay. So, the more wicking the surface is, the more liquid I can get into the nanofins, and therefore, more vapor I can produce. So, there is one theory out there that says it is the wickability, how wicking those structures are, that determines how much CHF you can get out of them. But there was one experiment that has discredited the wickability theory. I did not get to discuss all those, and that experiment showed that you had hydrophobic nanostructures, which is not supposed to wick liquid, okay, but it was giving CHF enhancement. So, then how is the wickability theory true? Okay. So, then one way you can explain it is, well, if your contact the surface tension changes in a nanobubble, maybe the contact angle also changes on those nanostructures. Okay. So, what we are measuring on the macro scale as a hydrophobic surface, once you make nanofins out of them, maybe under certain circumstances they are actually wicking. Okay. So, but that is a like indirect way of holding your nose kind of. Okay. So, there is a theory called wickability that treats these surfaces as nanoporous surfaces, which means if I form nanobubbles and these nanobubbles keep feeding into this big bubble, okay, then maybe the wickability of that structure makes sense, because as soon as a nanobubble forms and leaves, the wickability determines how fast the liquid goes and fills it up before the next nanobubble can form. Okay. So, there are probably unknown issues that we have not looked at, but from the current experiments that we have, this is how the structure looks like right now. You have a bunch of these tiny hairs and you have this big bubble on top of that. Does that make sense? Okay. Any other questions? Last call. Well, and you all have my contact information, you are welcome to send me email. And so, one word of advice, if you contact me by email, please make sure to include your contact phone number, and for the next 3 or 4 days what are the good times to call you, because sometimes it is easier for me to give a quick call, have a 5-minute discussion, than write a 2-page email. Okay, because you write a 2-page email and you confuse the person even more, because you write it thinking something else and they interpret it in a certain way. It is like the problem I gave you. I thought I gave you a 2D problem, and you guys thought it was a circular pipe, right. So, my communication was not clear to you. So, sometimes you write emails and the communication is not clear, isn't it. So, it's I figured it's better to call and have a discussion than write a long email. So, if you contact me and write a question, please include your contact number and the time to call you for the next 3 or 4 days, and I will pick a time that is suitable and call you probably. But if it is a short email, I will probably respond with a short email. Okay, is that clear? Okay, all right. Thank you very much, and enjoy the rest of your afternoon. All right.